And for those that missed anything yesterday, I posted to the YouTube. So if you search on TFRSAC 2022, those should pop right up. And okay, I'm going to dismiss that banner there. Okay, we're up over 30 already. Well, we're right at the top of the hour, so I'm going to go ahead and turn my camera off. If other folks would too, except for Birgit. Take it away, Birgit.
All right. Good morning, everybody. Welcome to the second day. Tactical Fire Remote Sensing Advisory Committee meeting. We had a good day yesterday. And welcome everybody back. I know we're going to have a few more people trickling in. We will note, I think Everett just said, but for those who are still joining us, that this is recorded, so just please be aware of that. And Everett, do you want to go on and advance the slide to the next one? Just a quick recap for those who are joining us today, maybe for the first time. TFRSAC has been meeting twice annually since 2003. I am a new member to the leadership group here, so I give a lot of credit and thanks to Vince and Everett, who've been driving this for the last 20 years, nearly 20 years. I've sat in on this quite a few times as a participant, both presenting and just as an audience member, and I have found this a very, very informative series of conferences and meetings. So much appreciated. Our objectives, again, are to demonstrate evolved and evolving technologies for increasing the information content and timeliness of EO data collected for wildfires. And we saw the wealth and breadth of that yesterday, and I'm sure we're going to see more of that today. So please, and I think also just if you're interested in presenting in the future or you have any feedback to us, please contact us after the fact. Our contact information has been shared in different venues and email and probably shared at the end of the meeting as well. Go next slide, Everett. Yesterday, we had some agency briefings from various institutions. We had U.S. Forest Service, USGS, NASA, Canada. We had also the final session of the day was about decision support tools and EO applications, and also saw a good cross-cut from the private sector, which was really interesting. This is one of the few conferences that I know of that actually really meshes both private and public sector, I think in a very informative way, and provides good communication between those two groups. Today, we're going to be hearing about fire behavior, fuel structure and assessment, energy release, ember detection. You can see the other topics here. So again, a good cross-cut in our two morning and early afternoon sessions, 4 and 5, and then our afternoon session will be getting some updates from the Purdue fuel team, and then fire and hydrology connections, the Fire Grand Challenge, and other speakers this afternoon. So if you can join us throughout the day, please do. We do understand that your schedules are probably packed back in and forth, but please come and attend as much as you can. See those via YouTube channel shortly after the conclusion of the meeting, and Everett has already posted some of that. For those of you who are speaking today, please be mindful of your allotted speaking time. We are a little bit jam-packed. We do have a little bit of wiggle room, but the better we can stay on top of our time, the better off we'll be. We have some speakers who need to be in other places, so we kind of need to stick to the agenda as best we can. Please keep your cameras off as much as possible. If you're speaking, you're certainly invited to turn yours on, but just to conserve bandwidth, we're asking anybody who's not speaking to please keep your camera off. We will be providing email contacts for the presenters after the meeting, but please don't use those for solicitations. They're really for information sharing purposes only. We've already said that the presentations will be shared within a couple of weeks after the event. Do let us know if there's any reason that you don't want your presentation shared. I know some people were talking about pre-release or pre-review data yesterday, so please flag any of those that you don't want to have publicly shared. And then finally, if you have any questions that arise, especially as pertaining to the talks today, please share those in the chat. One of us will be monitoring those chats, and if there's chances or opportunities after the after our speaker. If there's a few minutes between changeover, we'll handle those questions then. Speakers have been wonderful about addressing those questions in the chats after they are done speaking. And then we also have some sessions available today just for open discussion. So maybe we can use some of those questions to inform those as well.
Next one. We can probably breeze over this one here. We'll make sure that this.
Some nice recent and upcoming events. So, all right.
And I just grabbed a couple slides from the end of yesterday that kind of talked about some of the things that really needed focus, and so we can either talk to these or save them for later. There was Zach Holder, our keynote for the Forest Service, talking about data standards and interoperability. How do we communicate what the needs are? And you can see the other things there. And then this came from David Green from NASA, looking from the wildfire program. Sean Triplett had some. I love this slide here about technology is just one piece of the puzzle, and we have to keep that in mind as we have our conversations. And then this came from Intera and Techna Silva, and talking about what the TFRSAC can do, to help. And you see interoperabilities in every single one of those bullets there. Agency interoperability, effectiveness, company interoperability, and technology interoperability. So I thought those were really good points there.
Great. Thank you, Everett, for the quick recap.
And can I make one, thanks, Birgit. Can I make one quick comment also? We noted on that chart yesterday the upcoming events. I just want to point out to everybody that a recent event coming up is next week's conference in Pasadena. God, my mind just got lost. International conference on
Fire research.
Well,
No?
Yeah. No, the International Association of Well and Fire. Sorry,
Right.
These conferences all darkened up in my head, and I couldn't pick out which one was next week. So in Pasadena, California, next week, and one of the things is NASA is going to be a major sponsor of that conference, and we'll have a very large booth and exhibit hall. And we invite anybody that's going to be at that conference to come by and chat with us. There's going to be about 20 of us from various NASA centers, NASA headquarters, to interact with and to discuss our new program. It's kind of our coming out party to the wildland and fire community. So we want to invite everybody to that meeting next week. And if you're interested, we are going to be doing lightning talks in our NASA booth from community members that focus on use of Earth observation tools, geospatial tools, in supporting wildfire management, research, and application. So feel free to contact me if you're interested in doing a brief lightning talk, a 5 or 7 minute talk. And our agenda is filling up fast during those break sessions. And so maybe we can fit you in, but at least come and talk with us and our partner entities that will be there. So thanks for that.
Great. Thank you. All right, with that, I think we are ready to start into the technical part of the program. I'm going to ask Richard or Gus, could we do a quick sound check with you?
Hello.
Hello, we hear you.
Okay.
Can you hear me too?
You can hear you too.
Yes, I
Right.
sure do.
And I'll advance the slides. So
Okay. Well, good morning, everyone. It's a real pleasure to be here. Gus and I are excited about sharing our work over the last 3 years, which has been, our mission has been to raise community wildfire consciousness to a level that results in action for fire sustainability or community sustainability against fires in the 21st century. Next slide. Next, okay. My relationship with wildfires is close and personal. I started off as a hotshot heliTAC with the U.S. Forest Service and went on to be a fire researcher at the Forest Fire Lab in Riverside. Had the good fortune to be mentored by Clive Countryman, who was a renowned fire behavior officer in the Forest Service, and to study fuel conditions that led to extreme fire events. I also had the chance to spend over 20 years mapping fire disasters, earthquakes, floods around the world. So I've learned to see a lot of what people do in their environment. Next slide. Having survived wildfires, almost being burned alive, I kind of came away from the experience with a new view of wildfires. They are destructive monsters, or I'm thinking of a different word, but anyway, beasts. They're ferocious, destructive beasts that are on the increase. They're actually growing in size, they're growing in ferocity and destruction. And as such, I've had to consider how much we as people contribute to this problem, namely by feeding the beast. And we feed the beast by creating very flammable conditions in our communities that are just a time clock or time bomb before destruction hits. Next slide. There we go. Case in point is looking at Rancho Bernardo, the Trails community, where we have up in the upper image a normalized green vegetation map showing green vegetation cover within an area of the neighborhood. And in contrast, we see below it a slide showing mostly blue and only a few remnants of green vegetation cover left. We also note that the X's denote completely destroyed homes. There's 13 in this view alone. There were 77 total in the community. The idea is that we are setting up a problem in advance that has led to catastrophic losses, including life. And we seemingly are not aware of what we're doing, because if we look at it again, next slide, please. Yep. A series of time images starting in 2005, before the fire hit, again using normalized green vegetation cover as a cover map. We can see the abundance of vegetation, receive virtually no defensible space, which is required by law. We see how many homes in and around the vegetation were burned. And we see when Gus and I teamed up in 2018 to refly the same area, we see a reemergence of the same conditions that were the cause of destruction in the first place. So this series also shows us in concrete terms that science and technology alone are not going to break this cycle. They can stop a fire, but when people resort to old habits, they go back to the same mindset that they started with. They're setting themselves up for future disasters. So we are here to break that cycle of denial. And that's what it is denial. Next slide.
Is it showing up there, Richard?
Yep, we're right on track. Thank you. In 2019, we partnered with the community of Rancho Santa Fe in San Diego County, one of the most affluent communities in the United States. And we created 3 series of maps: the strategic maps for community level planning, defensible space maps for parcel planning and coverage at the landscape level, and change detection maps to monitor wildfire hazards over time. In fact, this is our biometric of looking at how much more defensible space is added each year over a series of years. Right now, 5 years, and moving into a indefinite period of reef sampling to measure changes. Next slide. Core element of this is our multispectral imaging at 5-inch ground sample distance. We are using NDVI, atmospheric resisted vegetation index, other indices that we have also developed. And then we're looking at vegetation cover, structure, and condition in proximity to structures and houses. Next slide. We've also created a new protocol for taking multispectral imaging and bringing out more information through a thematic enhancement. In this case, looking at the reddish area in the central part of the image is the about 100-year-old chaparral with upwards of 50% mortality. This is right in the neighborhood of million-dollar homes and the community or the city center of Rancho Santa Fe. It is so extreme in danger that the fire department will not respond to a fire in this area. And so we have a time bomb waiting to go off under the worst conditions. So I know about hazards and probability, but this is just setting a benchmark for what will change at whatever time. And again, probably under the worst conditions we can imagine. So what can we do to break this cycle? Next slide. We can further model the vegetation in our community, and using like FARSIGHT or other raw thermal-based fire simulation models, we can go in and look at very what-if categories of fire activity, fire behavior. And again, work with homeowners to visualize these consequences before they happen in reality. Next slide. We have then also a fire hazard map that shows the extremes in this community shot, going from low fire hazards with the green irrigated golf course, the light blue to dark blue non-vegetative surfaces, to extreme being the chaparral, decadent chaparral in burgundy color. There's the shades in between, and we see different canals or channels that fire uses to spread within the community. And we look at this under both a diurnal pattern of onshore winds versus Santa Ana with northeast winds. And we've clocked up to 50 to 75 mile-an-hour winds in Rancho Bernardo and Rancho Santa Fe, 50 miles an hour during the Rancho fire itself. Next slide. And so again, how do we measure our success? One parcel at a time in this case. We have a change detection image at 5-inch resolution showing the difference between 1 year taken in July, and the red is subtracted vegetation. And that's what we're looking for on a wider community basis. One homeowner doing the vegetation management to reduce the fire hazard is not going to save the community. Again, this will be an issue of taking the science, using it to leverage education, using education to change the mindsets of people to live with fire instead of against it. And I'll turn it over to Gus now.
Thank you, Richard, and good morning, everyone. My name is Gus Calderon. I've been a commercial pilot for over 25 years. I've been doing aerial imaging with Richard now for the past 5 years. My background is in earth science, actually in geology specifically. I also have a background in community management, video production, and editing. Next slide, please. So Richard and I, we've learned a lot of lessons over the last few years, engaging with the community, bringing them this high resolution data. So I'd like to categorize it into 3 areas. The first area is about the scale of the data for the community. The other area is basically the spectrum of homeowners that we've encountered in helping them manage their defensible space compliance. And finally, how to engage the community for wildfire preparedness. Next slide, please. So we have found for, remote sensing data at the community scale, it really needs to be high resolution. Specifically, that's a term that might be overused, 5-inch GSD from an aircraft really seems to be ideal. We have a lot of feedback from thousands of homeowners who agree with that. We also, as Richard has shown, it provides height data as well for 3D models and rendering, which is also very helpful in communicating with homeowners. The resolution of satellite imagery is simply too low for the parcel level, for the parcel maps, and at the landscape level. Also, even though I have a background building and flying drones for over 12 years, drones, I know this for a fact, they're not welcome in the community for aerial mapping. The public approval of drones is still single digits, if that. However, drones can be very helpful for ground truthing in unpopulated areas, and obviously they're very useful in wildland areas. Next slide, please. So this is what we call the homeowner spectrum. We have found that when it comes to defensible space, homeowners range from compliant to defiant. Even before we started our mapping 3 years ago, we found that some homeowners were already compliant with defensible space regulations. It was fantastic. It was really nice to see. Then as we started getting the message out to the community, others wanted to comply after they learned that we would be annually flying over the community and documenting the vegetation year after year. Then there's another area of another group of homeowners who were interested in complying, but they did not know how. This is an area that we are really focusing our attention on, because we found that if we can bring in the right experts, whether they're arborists or conservationists, ecologists, landscapers, whatever, we can help, because we don't, we're trying to attack a problem here that's on private lands. We don't just need homeowners' permission, we need their cooperation, and that's really hard. So we found bringing in other people is really helpful in that area. So another part of the homeowner spectrum that we've encountered is people who are very concerned about their privacy, and also who is going to see their aerial data. So we're going to talk about that a little bit. And then finally, there are some people who just love their trees and they're not going to let anyone tell them what to do. So in that case, it's probably going to come down to enforcement. So working with the community, we've found that you have to find a liaison who's really dedicated to wildfire preparedness. This is just absolutely essential. Also, have to host and attend community outreach meetings. And we've also found customizing parcel maps and reports for the community is also incredibly essential. We're going to talk about that. Being open and honest about privacy concerns, just taking it head on and answering questions is really, really important to alleviate those fears. We also found, that it's just not possible. I know people talk about going in and training community leaders how to use their database. That just does not work. In reality, people don't have time for that. Staff shortages, everybody's just stressed out. So everything has to be self-explanatory, including the maps. And as I mentioned, we really need to create a team of experts in multiple disciplines. Next slide, please. So, how do you get homeowners engaged in wildfire prep? There are a lot of ways to do it. I've seen there's a lot of videos out there in general talking about managing defensible space, but they're really not community specific. And if you want to engage with people, you really have to show how this hazard will affect them. And so we've shown with video production, showing the community, interviewing community leaders, relating to the community. That's really, really essential. I think that's something that's been missing out there. Also creating parcel maps and reports for all homeowners. This is something that was proposed by the community, by Rancho Santa Fe. They wanted us to do it. We facilitated that. What we found that really encouraged neighbor-to-neighbor communication, which is absolutely essential in communities. It's one thing for an organization to reach out and try and get people's attention. That's already incredibly difficult. But if you can put something out there that encourages people to talk with each other, that is really the best way to get a response. So we've been focusing on that area. Also using social media, web content, and you really need to create community-specific content. Tell what's going on, give reports, give updates, etc. Next slide, please. So after 3 years of working with Rancho Santa Fe, and actually another community as well, Like I said, we've learned a lot of lessons. So to summarize, the high resolution mapping imaging from the aircraft, it's really just ideal for the community scale. We found working with a team of experts in multiple disciplines is mandatory. Also, communication in simple terms. We struggle with this all the time. You know, as scientists, we're used to talking to each other, and that's easy. But you know, trying to communicate multispectral imagery and geospatial analysis to homeowners produces blank stares and gets nowhere. Community feedback, whether it's positive or negative, is absolutely invaluable. It's hard to receive that negative feedback. We have found that we actually would engage with a subset of the community, a committee, about 12 or 15 members of the community. And before we put any products or deliverables out to the community, we would run it by them to get some feedback. And that was really helpful as well, instead of sending something out to several thousand homeowners and getting a lot of pushback. So in the end, we found breaking the cycle of wildfire destruction really needs to be done one community at a time, and that is our mission. Next slide. If there are any questions, we could try and answer them for you.
Thank you for your very informative talk. I am not tracking any questions. Oh wait, one just popped in. So this is from Philip Byland. What strategies did you use with the public to allay their fears that this type of mapping would raise their insurance rates? And was the data made public?
I can answer that. Let's see. I can answer that. I think, on the contrary, what we're finding is that the increase in fire danger is the reason behind the insurance rate increases. The insurance companies aren't waiting for us to give them high resolution imagery. They already are doing their homework because they've lost so many billions of dollars alone in California. And so that has been an incentive for the insurance companies to start looking at people in high risk areas and even talk about not insuring their property at all. What we think in terms of having factual data, you can get your neighbors to chip in. This would be a community action that should help with liability, and it should help also allow other firefighters to go in and save homes instead of looking at it like this is a death trap. We're not going there. So that's a different kind of insurance, getting fire help when you need it, but it's all part of the game.
Thank you. And we're running a little ahead of schedule, so another question just popped up, and a couple more are, well, let's field one or two more, and then we can move on to the next speaker. But this is from Dave Jones. What kind of activities are you engaged in to get communities together?
Gus, you want to take that?
Well, we are just, honestly, we have over the last 3 years, we've really been focusing on our work with just a couple of communities to really refine what we're doing. And now we're getting to the point where we are starting to get the message out to other communities as well by public events, and finally reaching out to other areas as well. But this is a bit of a challenge. Honestly, it's pretty difficult to sell a scientific service to a community, most of whom are comprised of homeowners without a scientific background. So, you know, this is a challenge that we've had, but we think that the work itself and the satisfaction of the homeowners and the community leaders in Rancho Santa Fe are actually getting the word out for us. They're contacting other communities as well. So we're finding not just neighbor to neighbor communication now, but community to community communication as well about this program.
Unfortunately, we also find that when there's a major fire in the area, all of a sudden we get more interest. So there seems to be that, you know, catastrophic side. If it's going to hit you and be a catastrophe, you might get mobilized. We're just trying to get people to move before they see the smoke coming over the ridge.
Great. Thank you. There is at least one more question in the chat for you guys, if you might want to direct your attention there and give that give that an answer. But in the interest of time, I think we'll just keep moving along to our next speaker. Thank you again very much for that really informative talk. Our next speaker is Tim Ball from Fireball, and the topic of his presentation is characterization of fire geometry and energy release in relation to fuels geometry and consumption measured on the ground from the air and from space. Tim, can we do a quick sound check with you?
Can you hear me now?
Can hear you loud and clear, and I will monitor your time and I will pop back on video or turn my camera on at the 2-minute mark, just to give you a visual clue when you're running close to time.
Okay, thank you.
Thank you.
So thank you for having me. I'm going to report on the combination of two projects that I'm working on. One is the objects project in the CERTIP program. And CERTIP is a program that's DOD, DOE, and EPA funded program. And this particular grant is a grant to Andy Hudick, Nancy French, and Matt Dickinson of the Forest Service and Michigan Tech. They're sometime attendees of TFRSAC, and probably many of you know those people. The other component of the program is funded by the Gordon and Betty Moore Foundation, which is the effort to do this mapping of fire geometry and fire energy release, the radiative component of the energy release. Craig Clements and his group monitor the convective component of energy release. And the Moore Foundation funded the development of the thermal camera system in conjunction with the Forest Service in order to do this work. The satellite work has been supported by both the Moore Foundation, Ball Aerospace in Boulder, and the Space Dynamics Lab at Utah State and UC San Diego. Next slide, please. So the objective is to understand really the relationship between fuel consumption, energy release, both in radiative and convective terms. Obviously, they're linked, but how are they? Is that a really reliable? Is there a reliable relationship? Is it a changing relationship? Those things are not, have rarely been measured together, and they're not particularly easy to measure. And I think you'll see a little bit of that. One important question is, what's the split between where did the slides go? Sorry, here we go. Is the split between radiative and convective portions of energy release, and we know that varies, and we don't have a really good handle on the reasons and the extent to which that varies, and this is part of what we're trying to get at. All these things feed into both the development and the validation of fire behavior models, as well as smoke generation and smoke dispersion models. And that's really what the objects program of CERTIP is after. So I have the responsibility of measuring and mapping the radiative component. There are operational needs for these measurements too. They're not used operationally at this point, but my belief is that we don't understand the relationship between intensity and spread. The old nomogram, Rothermill's nomograms are still used today. They're an important tool for fire behavior analysts, and there are reasons to think that they don't really work that well. And a final thing that comes out of this is burn severity prediction. And we would like to measure that. We're trying to measure that prediction relative to the burn severity index. Next slide, please. Just a sort of elementary look at the relationship between consumption and energy release. We're on the next, here we go. There are really two approaches to this. One Andy Hudick likes to call the indirect model, which is basically looking at the subtracted biomass before and after the fire. Look at the changing biomass density, and then calculating a burn efficiency. And you can calculate the mass that way. And then if you've also measured the fire radiated energy, which is the time integral of FRP, then and know the combustion factor, basically how much biomass has to go into making a megajoule of energy, then you can get a separate value for consumption. Next slide. And the relationship that's thought to exist is a pretty linear relationship between combustion and energy release. And we're in the middle of trying to test that and see how that varies. Next slide. And so the other thing that I mentioned, prescribed burns, that the CERTA team, which amounts to almost 100 scientists, they're trying to measure all these things together. And we recently had exercises at Osceola National Forest in Florida and Fort Stewart, Georgia, and the military base at Fort Stewart. And a great number of people measured the vegetation parameters. And in particular, I had the responsibility of looking at the energy release from both the satellite and the airborne measurements. People from RIT did the ground measurements of radiation. Next slide. I think you can go on actually to 2 slides. Okay. So the next objective is to try to understand what satellites really see and why that's what they see. It's not very often that we get an opportunity to calibrate a satellite, and what is required to do that for a fire is to measure the whole fire the whole time. And that is not a simple task, but that's what we're trying to do, trying to put an aircraft above the fire and get that time integral of energy released. What you really want to do is then have measurements above from the satellite and below on the ground. And that's what we've been able to put together at these various prescribed burns that have taken place this spring and will continue next fall. And in the next few years, there'll be a whole group of these measurements. And then I have my relationship with the Moore Foundation and the development of a geostationary fire detection and monitoring satellite really needs these realistic measurements of what energy release is and what the satellite should see. And we are actively using the data collected at Fort Stewart to model and to validate the design of the geostationary satellite that we're in the process of developing. All these requirements take the ability to measure the fire with a non-saturating radiometric system. And we want both temperature and in-band radiance to be measured rapidly and at several spatial scales. And so next slide. The way I've done that is that I bought a pair of Telops thermal cameras. They're multispectral cameras. They've got 8 filter wheels, and I've set them up to measure specific bands of interest. For example, the 3.9 micron band, which is what the satellites all use as the fire band, and then long wave radiation to get the integral basically from 1.5 microns out to about 10 microns, and a series of neutral density filters in those filter wheels that prevent the system from saturating. So we're able to see temperatures up to almost 3,000 degrees. About the hottest that we saw at Fort Stewart was about 2,200 degrees. And the fires in Fort Stewart were not particularly hot. There will be some stand replacement fires in the future where it's really going to be challenging to get non-saturated images. But I think we're going to be able to do that. Next slide. Essentially, what the multispectral cameras do is measure radiation in specific bands and then also integrate that radiation basically to estimate the shape of Planck's curve. It's not all aspects of the fire are really Planckian, and so it's important to measure some of those places where there's not much radiation and where there's a lot. So this set of, there's a pair of multispectral cameras that do this to get a wide swath so we can see the whole fire the whole time. Next slide. Here's a picture of the multispectral system in the helicopter express ship that I flew in Fort Stewart. And next slide. And the next slide is just a picture looking over my head down onto the fire from what you jumped to, but never mind. The previous one was just a perspective from the helicopter. There you go. You can see the camera being pointed at the fire as we flew. We flew at a variety of altitudes. We were trying to fly at 10,000 feet, but there were predators up there doing military exercises, and so we couldn't go above 8,000 feet for the first 2 days of burn. And the third day was cloudy, so it was difficult flying. Okay, next slide. What we actually get while this system is operating is a set of 8 different pictures. The pictures are taken about, they're 1,000 frames per second in this camera. Can you move to move to the next slide? Wow, that's 2 of them, sorry.
Oh, sorry, Tim.
That's all right. There we go. So this is really what I'm looking at when I'm flying the camera. These images are the major ones from the set of bands on one of the cameras. The top left picture is basically what you would expect to see from most thermal cameras. So this is a very broadband camera, 1.5 to 5.5 microns, and there's really no neutral density filter in there. And this image often saturates. There are often pieces of saturation in there, and you'll see these in those images some images I show you, where it's green. That particular image is saturating. But because there's a series of neutral density filters, we can stack those images. So you subtract out the areas that are green, and then you put on the next highest filter image. And if that's saturated, you pull the green off of that and put the highest temperature filter on top. So that's how you build a HDR picture, a high dynamic range picture. It's what your cell phone camera does all the time. It does that automatically. And the other important one is the top middle one here, which is where we're measuring the 3.9. It's really 3.7 to 3.9, which is very close to the band that all the satellites use. And actually, there are some places where right in here, there was a little saturated area. And what that means is I'm going to have to reconfigure the 3.9 band so I don't get saturation. I'm going to need 2 of those bands. And that's good because it's pretty reasonably cheap to change those filters. Okay, next slide. I just have a series of kind of pretty pictures here of what you see. This fire was ignited by helicopter dropping ping pong balls. And what you see here are the lines where the pilot flew and dropped the ping pong balls. And the green here is saturated. And it's interesting because those are where the heavy fuels are. So in the Fort Stewart situation, you get basically what you get saturation from is little ovens where there's heavy fuels. The fire's in a sort of an area where it radiates on itself and then gets really hot. Next slide. So this image is what 16 goes east meso saw on the morning of one of the Fort Stewart burns. And this is basically like a seismogram that shows you the noise in the data from the goes east meso. And interestingly, we saw the first change in the goes pixels at 9 minutes after the first ping pong ball was dropped. And that was equivalent to about 2 of those lines from the helicopter dropping the ping pong balls. So we'll have the radiation measurement from the aircraft and then from the satellite. And the interesting thing about this is it shows you the importance of diffraction in the GOES imagery. These pixels are, a number of the pixels have fire directly in them, but these pixels on the side that don't have the red are places where the energy, the fire wasn't there spatially, but there's radiation spilling into those pixels from the diffraction of the optics of the satellite. So to get the true value of integrated energy that satellite sees, you actually have to take into account that diffraction and basically model it back into the pixels. Okay, next slide. The next 2 are just kind of pretty pictures that that's a pretty decent picture from later in the fire, and you can see how it's burned sort of from the edges. The center of this particular one is wetland, and it burned very, very slowly. Okay, next slide. And that's just I kind of like this picture. So it's a little bit oblique and a little bit lower altitude. You can see the trees in there, and again, those green spots are where the heavy fuels are. And when we really put the whole thing together, the green goes away because we have the HDR image. And another thing that you can accomplish, or you can, the idea of being able to accomplish this at very low scale. This is a series of images of the same place over a 6-minute time period, and this is in light fuels. It's basically low grass and some still live vegetation, and it's looking at the size of the flames as the fire spreads through that particular area. So we can measure the flame size and the rate at which it moves through that fuel. And since this fuel's been basically measured beforehand, we can put that whole relationship together. Okay, next slide.
This is the Fuegos slide.
Yeah, exactly. So Fuego Geo is Carl Pennypacker's nightmare that he had after the tunnel fire in Oakland in 1991. He's an astronomer that's looked for supernovae at the edge of the universe, and he thought, we ought to turn those telescopes around and look at the Earth. And we're in the process of developing a pathfinder of what we hope is a fleet of satellites that cover the world. We're doing this in the place in the world where there's the highest risk to lives and property from wildland fires, and that's the Western U.S. The satellite's going to have a 2.5 degree field of view. It's going to look basically from Tijuana to Saskatoon. There's about 250 million hectares in that area. And what the modeling predicts is that we will see a 1 degree Kelvin increase in the fire band, the brightness temperature, using the GOES WF-ABA algorithm, which compares 3.9 to 10.2 microns, calculates the brightness temperature, and you look at the brightness temperature change to detect and to measure the intensity of a fire. We can get a 1 degree Kelvin increase from a 30 square meter fire, which is a pretty small fire. It's about the size of we say a school bus, but maybe it's better to think about a semi-trailer. That's about 30 square meters. That's going to produce about 1 megajoule of energy, and that should give about 1 degree increase in temperature. That's about 200 times better than GOES. So the acuity of this detection is really good. The ground sample distance that we spent a lot of time agonizing against, like every aerial photographer, you have to agonize against spatial resolution and coverage. And we've moved the field of view out, sacrificed some ground sample distance in order to get over the front range. All the time. The satellite can be tilted fact, it is tilted normal. You don't fly right overhead. You fly over the equator, and you're never right over on the latitude or the longitude you want. So you're always tilted. And in a springtime situation where there's fires in Texas and Nebraska, you will tilt to the right and cover that same area. We can actually change the tilt with a sort of couple hours notice. The satellite will deliver data at the cadence of 30 seconds, and that's about 10 times faster than GOES. And again, we're doing an HDR. There are 3 integration times that are captured every time there's a capture. So we can see both the tiny fires and the raging fires going on at the same time over this entire area. And importantly, this has a real operational value. Our real goals here is to be persistent. Time from ignition to attack and evacuation are crucial. In situations of raging fires in the Santa Ana, or typical of the kind of thing that you see in the Feather River Canyon, like the Camp Fire, if there had been a satellite that could deliver this, the town of Paradise could have been evacuated. It was very clear that that was going to happen, and if you could have measured all this stuff. And it also lets you, it's important to prioritize among fires. And so we're not just doing, although we do a lot of early detection with the alert wildfire system. This is not just early fire detection. It's because it's a constant stare. It's an idea of looking for the whole thing. Am I out of time?
Tim, yeah, we're pretty much
okay.
gone over time.
Okay. Yeah, that's fine. Okay, that's cool.
The
other, you can see the other pictures. They're just what the satellite looks like. So, thank you.
Great, and the presentations will be shared. They're online, so people can look through your slides. There are some questions in the chat. If you want to give those your attention, that would be great. And thank you so much for your talk. With that, though, we are going to move on to our next speaker, Matt Dickinson, talking about fire behavior assessment team ground measurements on wildfires and opportunities for remote sensing. Matt, can we do a quick sound check?
Can you hear me?
Can hear you loud and clear, and I'm going to turn off my camera and give you a 2-minute warning by turning it back on again. So it's all yours. Thank you so much.
Okay, yeah, thank you. And thanks for the opportunity to talk about the fire behavior assessment team. So just before I start, I wonder, Tim, if we can say, there's this Bob Essenhigh quote out there that rocket science is not wildfire science. It's less complicated. Can we say that space observation, or wildfire observation, is not space observation? It's way more complicated.
That's for sure.
Cool. Next slide, please. And next slide. So just some background here. The FBAT mission is to improve the knowledge about relationships among fuels, fire behavior, and fire effects on wildfires, and to support the application of that knowledge to fire and land management, and then also to promote firefighter safety and public understanding of wildfires, and in a long-term program. Next slide. So the kernel of FPAT value is that we work within the incident command system to collect coordinated pre-fire, active fire, and post-fire measurements of fuels, fire behavior, and fire effects. And next slide. It's a unique module. It's on-call module of experienced land management, fire operations, and research staff who are dedicated to the mission. And we're ordered through the incident resource ordering capability as a list of name requests. And FBAT is collateral duty. So we all have other jobs, many of us Forest Service, most of us Forest Service. And, so this is something we do as possible and as time permits. Next slide. So some history. It was established by the Adaptive Management Services Enterprise Team, and particularly through the efforts of Joanne Feitz Kaufman around 2002. And on assignment, incident support travel and time, which has been really crucial and is the only reason why, this on-call module really exists. Between assignments, we have had grants funding through the history. Currently, there's CAL FIRE and USDA grant funding that are supporting some of the work. There's also been internal funding and most recently Region 5, National Forest System and Fire and Aviation Management, and then the Northern Research Station is of the Forest Service as well. There's staff time that's contributed. The on-callers, the advisory group, they all contribute time. Research data archive staff do, and up until just recently and continuing also to some extent, the enterprise program is staff members are helping out. Stanislaus National Forest hosts the gear and the vehicle, and we also have university collaboration. Next slide. So next slide. Right, so some organization and methods. This is the organization of the FBAT group. There's a program manager, that's me currently. There's an advisory committee. There's an assistant program manager, that's Carol Ewell at the Stanislaus National Forest. We're hoping to fill an operations manager position. And on assignment, there's an FBAT lead overall, and then there's an operations lead, which is task force lead or division supervisor level typically. And there's a science leader, and then there's various on-callers that play different roles: logistics, equipment, data, report leader, and so forth. And there's communications. We're integrated into the incident. There's communications with the command and general staff, with the public information officers, with the operations section, with the planning section. Next slide. So the core methods are, there's variable radius tree plots. They're indicated by the dotted lines. There's rate of spread measurements, which are comprised of an array of fire arrival sensors, and then we use trigonometry to determine rates of spread. And there's soil heating and pre and post fire soil sampling. There are Brown's lines and belt transects for surface and understory fuels. And then there's we're using we have a video camera on each plot, and also a fire behavior package that's not noted here. And the video is triggered by fire arrival, which is really critical because you set up the plots and sometimes they sit for a while before they burn, and so it needs to be triggered by fire arrival. Next slide. Oh, excuse me. One more thing. Just wanted to mention we're working on methods, evolution right now, and one of the key things we're looking at is to get three-dimensional fuels and vegetation mapping. From terrestrial laser scanning, GoPro on the ground, personnel on the ground with using sort of robotic structure from motion approaches, and also from unmanned aircraft systems. And we are also planning to integrate severity measurements from unmanned aircraft systems from UAS based on pre and post fire imagery. So we're working on these. It's always a process to get new methods incorporated, but we're making a good start on it right now. Next slide. So there's deep experience here. 237 plots in the database that from 28 fires. Then there's special projects as well. Most of the fires of late have been in California, but there's also fires from other states, and hopefully we can sort of grow the program and work in other regions as well. Next slide. And thanks. So some program delivery. There's incident at unit and unit support. So for incidents, we're as requested, we will provide situational awareness information to fire behavior analysts, long-term analysts, incident meteorologists, and air resource advisors. And we're always looking on how to improve. A lot of times the latency, we're getting these plots, we get pre-fire information, then we have to wait till the fire burns over, then we can get consumption information like shown in this table. But it's, so we're always looking on ways to improve how we help the incident itself. But yet the long-term value of these plots is really probably the core value. Next slide, or excuse me, next click. There's a summary report delivered to units after each assignment as well. And this provides a record of fuels, fire behavior, and fire effects on the plots that can be, used by the unit and into the future to sort of better understand and sort of remember what happened on a given fire. Next slide. So more program delivery. There's information for training and outreach. There's a video archive that's just recently come online, and the videos have been used in firefighter training and public outreach, and also in university classes. And we hope now that it's available that it'll be more widely used. It's you can choose which fire you're interested in, which national forest, whether you're interested in backing or heading fires, or crown fires, or surface fires. So it's pretty convenient, and if you can just do one click, sorry. Yeah, so here's two examples from the video archive: a creeping fire and a 2016 maple fire, crown fire in lodgepole pine that was sort of regenerating after the 1988 Yellowstone fires. Next slide. And again on training and outreach program delivery, there's for each plot there that has more relatively complete information. There is what we call a digital fire dictionary entry that summarizes fuels, fire behavior, fire effects, and the video and these summary sheets are available on our Frames website. You can just Google Frames and FBAT and it'll come up. So if you could click 4 times, appreciate it. So yeah, there's pre and post fire photos, there's fuels, topography, weather, fire behavior, and fire effects on these plot summary sheets. And then you can tie those back to the video. It's super interesting and enables you to really understand what went on, at that particular location. We have been in discussion with the fire EGP to get these up online, so someone new in a region can come in and look at past fire behavior, in the off season, or potentially an FBAN can look at this information, as they're working on an incident to get a better sense of what's happened in the past. Next slide. All right, so it's also critical and that we sort of complete the full cycle of research, which for me and my role is sort of starts and ends with publications. If you can, I think, click 4 or 5 times, there's there's a number of papers published and in review or in press currently. We've got a postdoc working on the project from Michigan State that's making great headway on the data set, and has revisited all the plots or all the ones that are pick up some more of those. But it's key to publish, and so we're making headway on that. So next slide. Another key thing is FBAT provides a core set of measurements that really valuable for add-on research. For instance, we've supported Jessica Meisel and Aaron Hanen from Michigan State and University of Nevada, Reno, respectively, in soil work from our wildfire sampling. We've also supported Jonathan Greenberg from the University of Nevada, Reno on his 3D fuels and forest structure and fuel consumption monitoring. And we're trying to integrate, again, more of that 3D information into our sampling as a standard thing from here on. Next slide. I'm going to show a few examples of results and use of the information. This is a series of photos from the Willow Fire. It's the same location, each time, pre-fire, post-fire, within days of the fire moving through. And then in 2021, so this Willow Fire burned in 2015. So, and this was from space, it was moderate severity. And yet, if you click one more time, what actually happened was, in the 6 years between 2015 and 2021, it's essentially, became a stand replacement situation. So, which you would not necessarily have predicted right after the fire, because the effects, the scorch heights, the consumption of crown, levels were low to moderate, although there was a lot of fuel consumption. So that, this was in the middle of a drought, and so trees are stressed, and I suspect that's a lot of the reason why it ended up this way. But these kind of data, you know what the fuels are, what the fire behavior was, what the immediate effects were. You can come back and look at longer term effects and explain what happened and why. Next slide. So here's another result. So if over the whole data set, if you're interested in what are the main contributors of fire energy, and which is proportional to consumption and emissions, it's really the litter and duff. That's in pink. That's contribution on the y-axis to total consumption. And then it's woody, large woody material, 1,000 hour and plus. So it's key information for air resource advisors. And if you want to figure out how to reduce emissions, this is good information to know about. Next slide. Another interesting outcome from the pre and post fire data set is heading fires consume more litter and duff than backing fires. There's this anecdote in prescribed burns that backing fires are consuming more fuels, they're longer residence time, they're heating the system more, heating the soils and trees more. That may well be a myth, and there's just no great data on it. But in wildfires across our data set, backing fires have lower consumption of duff and litter than heading fires, and this is not related, in a general way to weather and pre-fire fuels. So, okay, all right, remote sensing. There's a number of connections here. Clearly, improving fire severity mapping and its calibrated products, biomass loss soil effects is a good use of these data, and we're working on that. Also, the ground calibration data could serve to support fire scales or whole fire studies on fire dynamics, suppression effectiveness, both ignition operations, or firing operations, and airborne aerial suppression, and also an understanding of fuel treatment effectiveness at sort of this whole fire scale. We know a lot about what individual treatments do, but we don't know a lot about how collectively they impact fire dynamics. So, some potential, ways to integrate this kind of ground measurements in these broader scale projects. So, and also sort of the FMAP model, which is integrating into the incident, is, I think, really key for getting tactical information on incidents that's otherwise lost to posterity. And there's a lot we'll never understand because the kinds of information you need, where the firing was done, when it was done, and so forth, are just not collected. And anyone interested in this kind of thing and learning how we might expand the program, I would love to talk with them. And sorry I went over a little bit. Thank you.
Thank you, Matt, for a great talk and a different perspective, which I certainly appreciate. And I think I for sure will be following up in the not too distant future. So I don't see any questions in the chat right now, but maybe keep monitoring that because it seems like sometimes those trickle in after a person stops speaking when people have a chance to think about everything that you just presented. So maybe keep your eyes on that and answer those if they come in. So thanks again. We will move on to our next speaker on our next talk, which is going to be about UAS-based grass fire metrics measurement. This is from Dr. Tian Chao. Can I get a sound check from you, please?
Yeah. Hello, can you hear me?
Hello, we can hear you loud and clear. Thank you so much. I'll turn this over to you in just a second. I'm going to turn my camera off. I'll give you a 2-minute warning by turning my camera back on. So in the interest of time, I'll just let you go.
Thank you. Yeah. First of all, thank you for the opportunity to give a talk here, to introduce our progress on small UAS-based grass fire metrics measurement. For the grass fire metrics measurement part, we actually mean fire from location as well as the fire rate of spread. So for me, for the background, I'm a associate professor from aerospace engineering department at the University of Kansas. My background is actually on the sensing, estimation, and the control of unmanned aircraft system side. Okay, so on the left of the picture, you can see is actually a fixed wing aircraft, 5.8 pound, roughly 55-inch wingspan, fixed wing UAS. We used to collect thermal data. On the right, you can see is actually example thermal images we collected during one tall grass fire burning experiments. So within this talk, we're going to show you guys how we convert these nice looking pictures into the fire metrics, such as rate of spread. Next slide, please. So the overall outline, introduction, UAS platform, and then fire from location as well as fire rate of spread measurement using UAS. Lastly is conclusion and future work. Next slide, please. So one thing we want to point it out, for our experiment, we actually did it, through controlled grass burn. We feel, millions of acres, Kansas grassland are burning or have been burned, each year. It's actually, we feel this will be ideal a simulation environment so that you can test, your new generation, fire sensing or fire fighting, essentially instrument. And then, the UAS can measure many things, for such as, fire from location, rate of spread, flame height, fire intensity, wind speed, pre-burn biomass, all these metrics. And we feel a combination of, ground, UAS, manned aircraft, and satellite together will do a much better job, than using it alone. So essentially, within, our fire rate of spread, some challenges for UAS-based fire measurement essentially is we can see is actually, usually speaking, for controlled burns, still, this high temperature, strong wind and turbulence, smoke and the fire plumes, all introducing a lot of, difficulties for, pilot or ground control station operators. Okay, however, for a small UAS, if it's well planned, you can provide, high spatial and temporal resolution, images. Okay, so on the right, video is actually taken by a DJI, quadcopter. So close to the end of a controlled burn, the same controlled burn data we fly in addition to the DJI close to the end. We also fly our fixed wing aircraft in the middle, and we'll want to show you guys how we generate that data, convert that to the rate of spread measurement. Oh, Next slide, please. So next slide, yeah. So our platform is, I mean, as I said, 5.8 pound. We have kind of like two main payload. One is like FLIR View Pro R, thermal camera plus GoPro NIR. We modified the filter, okay, to make it 850 nanometer band. The endurance of our aircraft is 20 minutes. We are powered by a Pixhawk Cube autopilot. The strongest wind we have flight is like about 15 miles per hour. So our cruise speed is roughly 25 to 30 meters per second. Something we want to point it out, the difference between UAS, especially small UAS and manned aircraft or satellite is, kind of essentially the accuracy of the sensors. Okay, next slide, please. So for the georeferencing purpose, you do need the X, Y, Z and 5 theta psi. For open source, autopilot, your accuracy is fairly, not that great compared with manned aircraft or satellite. The position maybe 1.5 meter horizontal CEP error, and then orientation maybe, several degrees or maybe 1 or 2 degrees. And then this will introduce, some challenges for georeferencing, okay, so which we will try to address later through essentially staging, structure from motion. So the two example, thermal image and the near infrared image over the controlled grass fire burn, you can see, one is on the left, the thermal imagery actually, kind of like after some post-processing, you can get the temperature out, okay, the NIR image, as you can still see a lot of information. However, sometimes you will be kind of like the smoke will get into your view. Okay, similar problem is not that great for the FLIR View Pro thermal camera. The band for the thermal camera we are using essentially 7.5 to 13.5 micrometer. However, for NIR it's like about 850 nanometer. Next slide, please. So the problem we are looking at essentially is the fare front location as well as the rate of spread measurement. Okay, so essentially from our literature review, we have seen kind of a lot of people are using manned aircraft. Some people are using satellite. Very few people are using UAS, especially on some people are using quadcopter UAS. I think very few people are using fixed wing UAS. The advantage of fixed wing UAS essentially you can cover a big area. And then, if few people are using fixed wing UAS, for small, kind of essentially the small controlled burn, applications or wildfire applications, then, the data processing or representation part is just not there. So which is something we are claiming. Can you click on the thermal kind of video? So you can see on the left, essentially, this is a thermal video. Thermal image, actually, we staged it into the video, it's 1 hertz, and then you can see it's with the time going, individual image. And then on the right, essentially, we are trying to stage them into the fare map such that, we can derive the fare matrix. Next slide, please. Yeah, so the experiment we are talking about is it's a fall burn, October 8th, roughly flat area over 615 by 350 meter tall grass, area. It rained like 3 days before. The wind is measured by a ground wind anemometer. It's roughly 13 miles per hour from the south. We have 2 fare sighting crews. Both started roughly in the middle of the north boundary, and then one team clockwise, the other team counterclockwise to set up the fare. Okay, so they meet roughly in the middle of the south boundary. Okay, we fly our UAS 120 meters above the ground level. Our trajectory is shown on the bottom right figure. It's actually our ground control operation operator, GCS operator. He's actually adjusting the flight path dynamically, because the fare is actually going, and then we cannot pre-plan the flight path, that well. So we doing kind of during the fare burning adjustment of our flight path. Okay, next slide, please. So the overall procedure we're talking about is essentially kind of like we can divide it into 3 blocks. Number 1, we call it multi-temporal also mosaic generation. Okay, so given individual image, we divide it into multiple loops. I mean, kind of then, within each loop, we use IDSoft to do the also rectification. And then after we get the map, we do registration. Okay. So then we move to the next block. We call it fair evolution mapping. Essentially, we detect the fair boundary, fair front location, and then we use kind of manual delineation to kind of get the fair front. Essentially, we are using kind of half, autonomous, not exactly manual, because we are using the threshold based. And then after that, we can calculate the fair rate of spread. Okay, next slide, please. So this is our generated also maps. Okay, so you can see one thing different compared with a lot of manned aircraft or satellite data is like we see each map. I put an interval there. It's not exactly a timestamp. Instead, this whole map is generated from 100 images taken at different time steps. Okay, so we are making some assumption regarding kind of how fast the fair, is moving there. Okay, but within each map, when we are calculating the rate of spread. Essentially, the footprint, for our UAS is essentially roughly like 160 by 120 meter. The whole area is 650, by 350, roughly like that. So essentially, it's, within each, footprint, your time is different. Okay. So, and then after our registration staging, we did a registration with a NIP image, and then we compare essentially with the horizontal root mean square error is roughly 2 meters. Okay, next slide, please. For our flight, because our planning, we didn't, and then our UAS endurance, we didn't cover the whole fair burning. The whole fair burning is roughly like 47 minutes. Our this particular flight is roughly 15 minutes, and 10 minutes of data is used for the, data analysis. And then after we get that, fair map, we can derive, essentially the fair boundary. We focus on the head fair and the flank fair, the back fair, essentially because the fair spread is going very slow. We didn't, focus on that. Okay, you can see we kind of essentially draw the fair vectors. The advantage for UAS is kind of better spatial resolution. Okay, so and then we did, quantify, cross-validate our rate of spread measurement with another information source, which is DJI. DJI is not great, but we managed to do some registration. Through our quantification, we found out roughly like kind of 9% or 10% error. Okay, next slide, please. And then our final forward, essentially head fair, rate of spread, kind of in the beginning is roughly 0.225, 0.22 mean ROS, and later go to 0.28, the maximal speed go to 0.4, and later we notice like close to the end is probably 0.45, or close to 0.5, but not 0.5 meter per second. And then on the flank, kind of fair, that rate of spread is much slower compared with head fair. It's only 0.11. It's showing on here. The details can be found in our journal paper. Next slide, please. So essentially, in conclusion, we feel, our low-cost method is proposed. Yes, it's great, for manned aircraft or satellite. Especially for manned aircraft, it's definitely costly. It's also dangerous. Okay, so we generated, the fair map. We calculate ROS. We haven't seen, remote sensing based measurement of tall grass rate of spread measurement. And we published our kind of essentially our thermal map, the final thermal map. We published on our kind of website. We can whoever interested in, feel free to send us emails if you want high resolution. To looking into the future, we did it on controlled burn. If we want to go to real wildfire, what do we do? It's actually similar technology. My colleague, Dr. Barrett, he has a patent on ultra robust UAS can fly at 130 mile per hour. Gust UAS. We can adopt fair sensing plus ultra fast UAS. Next slide, please. And then some other application. Within this slide, everything we are talking about is doing post processing. Can we do real time analysis? There are some methods such as SLAM based method. Next slide, please. And also some low-cost solution, for example, using near-infrared, camera, that low-cost data. There are pros and cons for thermal versus near-infrared. Resolution-wise, NIR is better. Temperature-wise, probably thermal is better. Okay, but I think low-cost is definitely a good advantage. Next slide, please. And lastly, I would like to acknowledge the funding support from USDA NIFA, National Robotics Initiative Grant, NSF, SCC grant, and KU Research Go grant. And also this talk is a summary of all my collaborators, essentially all my students, all my collaborators, and the Kansas Biological Survey. Okay, that's it. Thank you. Yeah.
Thank you so much for that talk. You packed a lot of information in there. We appreciate it. I'm not seeing any, I think we just got one question that came in. In the interest of time, I think we're going to have to move along, but if you can address that in the chat as you have time, that would be great. And thank you so much, Hang, again for your talk. Now we will move on to our last talk of the morning. We are going to be hearing about deep neural network with Walsh-Hammerod transformed layer for ember detection during a wildfire. And can we do a quick sound check, please?
Testing.
Yep, we can hear you. Thank you so much. And speaking will be Anisetin. And I, again, in the interest of time, will let you go here. I will turn my camera on when you'll get a 2-minute warning.
Okay, thank you very much.
Thank you.
This is a joint work with Adam Watts. He's at Pacific Northwest Research Station, U.S. Forest Service, and we are electrical engineering and electrical and computer engineering people at the University of Illinois at Chicago. Next slide, please. As we just heard from the previous speaker, UAVs can monitor the fire front. We also believe that they can detect embers coming from the wildfire, and we will focus on amber monitoring here in this talk. And they can provide, if you install an IR camera or even a regular camera, you can get real-time information from the fire front, and you can determine where the embers will be landing. So we developed a neural network which can automatically detect embers in wildfires. And I have some experimental results at the end of my presentation. Next slide, please. There is no need to preach why we need amber tracking and detection in this to this audience, but we are going to present this paper to an electrical engineering conference next month. So we prepared this slide for them. Embers can travel miles in the wind, and they can cause wildfires to spread not only quickly but also unpredictably. And if we can detect and track the embers, we can inform the firemen in real time where the wildfire is spreading. And that's the main motivation of this research. Next slide, please. We developed a neural network for this purpose. We are using the currently available neural network architectures. However, we modify them. We don't use them as they are. And as you will see at the end of the the presentation, our neural network architecture provides better results than the regular neural network architecture. Next slide, please. And we use the Walsh-Hadamard transform in our neural network. Walsh-Hadamard transform is a binary transform, and it can be used to perform approximately perform the convolutions in deep neural networks. Next slide, please. And in neural networks, they use ReLU, rectified linear unit. We don't use the rectified linear unit in our network. We use something what we call smooth thresholding. And this is the graph of the smooth thresholding. Next slide, please. And we revise the standard ResNet architecture to detect deep to detect flying ambers. Next slide, please. Okay. Now, this video clip is obtained by Adam Watts in 2019 and 2011. And so we can see the fire front here, and the small ambers are leaving the window here. It's amplified on the left, and fire pieces or wood pieces are flying. The video is obtained using a FLIR shortwave infrared camera using a DJI drone, and we have various video clips obtained from 50 to 120 meters in Florida in October 2019 and February 2021 in prescribed fires. Next slide, please. So now I have we constructed a data set to train the neural networks. And it turns out that you cannot just use a single image frame to detect the amber, because we have moving objects. So we should use video to detect the ambers. So for example, on the right image, there seems to be an amber region. However, when we look at the video of that green small window, we can see that it's different from the amber region, which is on the left. So temporally, you can distinguish the ambers or amber clusters from small spots of fire. You see these little hot areas on the right image correspond to small fire spots, but the one on the left corresponds to flying ambers. Now, this camera has a video resolution of 720 by 480, and the frame rate is 30 images per second. So we need a video. So we feed our neural network with a video clip, but we divide the 720 by 480 to smaller windows and feed them to the neural network. Next slide, please. And the video size is 64 by 64 by 32. So in each temporally we have 32 frames, but the window size is 64 by 64, and we divide the video into small windows of sometimes overlapping windows of 64 by 64, and we construct the training set and a test set. A training set and the test sets are different from each other, and we manually constructed these training sets and test sets to test our neural network and to train our neural network. Next slide, please. Next one, please. And we used various neural networks. So if we use just a single image frame, the neural network is not very accurate. Its accuracy is about 95%, just from the single frame. However, when we use a slice of data, the recognition accuracy increases from 95% to 98%. And then when we add our Hadamard transform layers, the accuracy increases to 99.71% in our test data set. It's almost perfect, but you know, the neural networks can provide really outstanding results, and that's what we observed in this case. Next slide, please. So in this talk, we show that we can automatically detect and track flying embers during a wildfire using a drone. In this case, of course, these are the video clips are obtained during prescribed fires, but we believe we can extend this concept to wildfire monitoring. And they can help the firemen to track the progress of the wildfire. The drone that we used had an SWIR shortwave infrared thermal camera, but regular cameras can be also used because the flying embers have distinct colors, and they can be identified in regular cameras as well. And we developed a novel neural network for detection that's based on the classical architecture of ResNet, residual neural network. But we introduced our own layers that improved our recognition accuracy, and we get higher true positive rate and almost no false negative rate in our architecture. Next slide, please. Okay, thank you very much for listening, and I would like to dedicate this talk to our friend and colleague Emilio Pineda, who passed away 2 weeks ago. Thank you very much.
Thank you very much for your presentation. Thank you all our speakers for your presentations in this session. We have reached the end of this block. I am not seeing any questions, or you might want to please monitor the chat if there's anything there. All our speakers, actually, I've seen some filter in later on, so as people have a chance to digest what they've heard, I think we get more questions, and then questions and responses to questions. Everett, Vince, is there anything you want to share before we go on break?
I did see a couple comments there for Amit there. So if you want to check the chat sequence there, and I guess that's all I really had. I'm sorry to hear about your colleague that passed. That name sounds very familiar to me. So, Vince, did you have?
I don't have any. I don't have any additional comments heading into the break. I was amplify what Everett had said in that, you know, please look at the chat session. There are some questions there for the various speakers, and then I see that some of the speakers have replied already in the chat. So great to have that conversation going and extending beyond. That's the purpose of our TFRSAC, is to stimulate conversations and interactions amongst the community, to look for partnerships and to develop new research opportunities, new partnerships, and new technology infusion capabilities. So with that, I guess we can head to break. And when are we due back? Let's see, we're due back at
1:05 Eastern.
1:05. Thanks.
Yep.
Thanks.
Yeah, I have that posted on the screen there. So if anyone comes in while we're on break, they'll know.
Great. Okay. Thank you. I'll be chairing the next block. We'll be starting up at 1:05 precisely. Thank you.
Thanks, everybody. Thank you, speakers.
because you wish to check your mic to see if you are muted.
Hey, Vince.
Hi, Everett.
Is Carrie Nicholson online? There she is.
You're muted right now, Carrie.
Hi, Carrie. Want to do a sound check? Try to, let's see. I can, yeah, I can't unmute. One thing you might try is log out and then come back in again if you just want to leave and then come back.
Can you hear me now?
Yeah.
Yes, yes.
Ah, great. Okay. Now
The
let's see.
video's frozen, but we can hear, oh, there's two of you now on my screen.
Oh,
The frozen Carrie screen and your screen.
okay. Sorry.
Always something new and different.
Yes.
We'll get started here in just a minute or two. Give people a chance to get back from lunch.
Great. Well, I'm glad we had the break to sort out my technical glitch.
Yeah, I love your opening slide here. It's quite eye-catching.
Oh yeah, I'll talk about it, but it was a really great memory for me watching EcoStress being installed on the ISS. You could see the robotic arm there, and
Right.
it was really great experience.
I bet
You
it
know, they
was.
pass it from different robotic arms and just hanging over the Earth.
Yeah, I've thought a lot about the EVAs that the astronauts do up there, you know, when they're doing maintenance or adding stuff. It's just amazing to think about flying over the Earth and at fairly high speeds.
Yeah.
Being outside the station, yeah. Free floating in a void.
Incredible.
Okay, we are at 1:05. So I guess we'll go ahead and get started. And so our first speaker in block 5 is Carrie Nicholson, and she's going to talk about applications of echo stress in the study of wildfire. I'm going to take my camera off. When you have 2 minutes left, I'll come back on to give you a visual cue that it's time. And so with that, I'll advance your slides.
Thanks a lot. I don't see the slides yet.
That is my bad. Let me, thank you. There we go.
There we go. All right. Hi, everyone. And thank you so much for joining us. I am very pleased to tell you today about EcoStress. And this image that you'll see is a photograph taken as EcoStress was installed on the outside of the International Space Station. You can see the robotic arm is holding it, and it is plugging it in almost like a giant USB drive. And so that was something that was really incredible to witness. That was back in 2018. So if you could advance slides, please. So EcoStress is a thermal radiometer, which means intrinsically we measure temperature, so anything from wildfire, which I'll speak about today, to volcanic eruptions, to urban heat waves. So that bottom right image there is a heat wave over Los Angeles, and you can actually see the heat retained in the roads there. Temperature changes in the ocean, and in the bottom there you can see some of the currents that are different temperatures here off the coast of California as well. And we also measure very, very tiny changes in temperature that can indicate plant stress. And so that image on the bottom left there, you'll see the blue round spots are irrigated fields. They're transpiring, they're using and releasing water, and the beige area behind it is not able to do so, which may indicate stress or barren ground. Next slide, please. So just some of the technical specs about EcoStrace. I won't dwell on these too much because these slides will be available, but we acquire data in 5 thermal bands. The products are available at 70-meter resolution. The temperature measurements are highly accurate, and we have a very wide swath, which enables a very fast revisit. And I'll go into that in the next slide, please. So because we're on the ISS, we have a really interesting orbit. The ISS is in a precessing orbit. So in the bottom panel there, you'll see the descending orbit in yellow and the ascending in blue. And you'll see that as we move to once we've circled the Earth in 90 minutes, the next time we come around, we're a little bit to the west. And in the main panel to the left, I've tried to illustrate what that means. And these are some of our acquisitions that were acquired over the continental US. And you can see that at about 9:30, there's that orange line. About 90 minutes later, at about 11 o'clock, there's that green line. You can see you've shifted a little bit to the west. And 90 minutes later at 12:30, you can see we've shifted further to the west and you have a blue line. But what that means is that there is the potential for multiple acquisitions within a single day. Obviously, that's more likely at high latitudes, but it can happen elsewhere as well, especially as the ascending and descending lines may cross. What's also interesting is that our overpass times differ with every observation, which really makes this a complementary instrument to the polar orbiters with fixed revisit times. We do produce data at night as well, and so it's great to see temperature of wildfires, amongst other things, in the evening through to the early hours of the morning. And so I just wanted to let you know a little bit about the instrument, the data that we produce, in the hopes that you'll be able to use it in fire applications. You go to the next slide, please. So EcoStrace was originally designed as a mission to monitor plant stress, hence the name. And so I just put some of the original objectives here, and we want to understand how plants respond to changing water availability, especially by monitoring evapotranspiration, or ET, which can be used as a measure of plant stress. Next slide, please. But of course, because the inherent measurement is temperature, we can use it for all kinds of things. So this is just an illustration of some of the EcoStrace imagery of wildfires in California in September of 2020. And all of these observations are within a single week, and they don't even capture all the fires that were detected. You will all recall what a bad fire season that was, as was the following season. And next slide, please. And we've worked with collaborators at the Pacific Northwest National Lab and the US Forest Service to use this data to monitor fires. And so here on the left, 2 panels, you'll see the bootleg fire as shown by an EcoStrace temperature image. On 2 different days, you can see the fire growing larger. And on the right, you can see the fire classes mapped in relation to some existing infrastructure. These are high voltage transmission lines. And so PNNL and USFS were particularly interested in monitoring this fire as it intersected with the transmission lines. And they found EcoStrace to be particularly useful because it was able to acquire that high resolution data, that 70-meter data, at times when the other instruments weren't available. And so they used this as a supplement to their airborne imagery that was acquired at night, and the polar images, the polar orbiting satellites as well. Next slide, please. So Bootleg ended up being the 3rd largest fire in Oregon history. And here I've just showed a GIF of the fire as it was detected by mapping the hottest EcoStrace pixels. And you can see how it's growing rapidly there. Next slide, please. Now, beyond mapping just the actual active fire front, we also use some of I'm showing the Bobcat fire, which actually happened quite close to my house in California. And on the top left, I've shown what we call an evaporative stress index. So the beige areas are stressed vegetation, and the blue areas are healthy, happy, well-watered vegetation. And so that top left panel was an image acquired about a week before the fire started. You can see an old burn scar there. That was from the Ranch 2 fire that burned the month before in August, and this fire burned in September. You can see that the area where the fire began was vegetation that was already stressed in the mountains. And in the next fire to the right, you can see how that vegetation stress shows up into, because it's now a burn scar. And we've superimposed some of the eco-stress temperature pixels on top of that to show the active fire front. In the bottom panels, we showed what that area looks like after the fire. And you can see that even 6 months after the fire, that vegetation was still obviously burnt and recovering. And so these are the sort of metrics that we can use to monitor recovery from wildfire. In the next slide, you can see the work of Helen Poulos. Could you advance, please? Thank you. And so she studied fire recovery at a particular site of interest, and you can see some of those images at the bottom. She found that in areas that experienced a low severity fire, the vegetation grew back relatively unchanged. But in areas that suffered from high severity fires, a lot of the pine, oak, and scrublands were replaced with shrublands in the regrowth. And that shrubland, if you look at that top left figure, you can see that the burn severity is at the bottom and the evapotranspiration is the y-axis. And you can see that those shrublands have a much higher ET than the other land cover types. That means they're using more water. So post-fire ET is an interesting metric showing vegetation recovery and water cycling. If you go to the next slide, please. This is the work of Madeline Pascalini Campbell and Christine Lee, who have been looking at eco-stress data to predict wildfire by looking at the pre-burn conditions. So in that left column on the top, you will see the burn severity, where those yellow areas show regions that burned with a high severity. And directly below it, you'll see the eco-stress ET. And you can see a fair bit of correspondence between these two figures. And what they found was really interesting was that it depended on land cover type. So in the grasslands which had high ET, that means that these grasses had enough water, they were doing well, there was a significant volume of grass that served as very good fuel, and the fire burned very severely. But in the evergreen needleleaf forests, the opposite trend was true. There where the ET was low, that means that these trees were dry, they were stressed. That was where the fire burned most severely in the forest. And so there's this interesting contrast between land cover types and fire behavior, but yet again showing that ET is a reasonable predictor, taking into account land cover type for burn severity. If you could move on to the next slide, please. So this data is available to everyone, it's freely available, and we really would like for all of you to be able to use it. So if you would like to use the data, there are a number of e-learning resources available on the Earth Data website. And if you go to the next slide, they also have a really useful tool called Appears. So for those of you who don't want to deal with raw data formats and you would like to have something just pre-processed and easily available to work with, this is where I suggest you go. You can Google it, it appears with 2 E's, or you can head to the website that I've linked above. You will need to have an Earth Data login, but it's free to obtain, and it's simply to monitor data use. There's the opportunity to extract the eco-stress data as well as other data sets. If you move to the next slide, please. In particular, you can extract areas. So that means if you upload or you draw a polygon, you can actually get GeoTIFF images of eco-stress, temperature, or other products. Or you can upload a single point coordinate or set of coordinates, and you can get a time series in a CSV file. If you can move to the next slide, please. There are a number of ways for you to upload your area of interest, either by typing coordinates, selecting a point on a map, uploading shape files or the CSV file of coordinates and so on. Next slide, please. And you can select a number of data sets. So if you type ecostress into the search bar, it'll bring up a number of ecostress data sets you may be interested in. Here, I'm looking at the land surface temperature product.
Sorry,
That's okay.
am I on the right one?
One down, please.
There we go.
Thanks. And you can submit your data query. If you can go one more, please. Thanks. So you will receive an email saying your request has been submitted, and later on you'll receive an email to say your request is ready for download. Next slide, please. And so what you'll get is something like the image on the right, which is a geotiff of an area that I requested, or a spreadsheet like that on the left. And you can see the columns for latitude, longitude, the date and time, as well as the product you requested. This is the land surface temperature in Kelvin, along with some quality flags. So you'll see where clouds were detected or where we may be concerned about the data quality. And you can filter those out if you're not interested in the cloudy pixels. We have products produced for land surface temperature, emissivity, evapotranspiration, evaporative stress index, and water use efficiency. And all of these are processed everywhere over land. The land surface temperature and emissivity are available day and night, and the other products are available during the day because typically the evapotranspiration is relatively low at night. And we really welcome users of this data because I think that there are a lot of important applications that may be relevant to wildfire monitoring, both in terms of risk assessment, fire monitoring during active burns, and wildfire recovery. And if you move on to the next slide, please. And one more, where to from now? NASA is also proposing a new Earth System Observatory. If you can go one more slide, please. Which will include instruments that will continue our thermal measurements. And I'm out of time, so I'll move to the final slide, which has my email address in case anyone would like to reach out to me. And I welcome your questions. Thank you.
Thanks, Carrie. This is Vince. I've got a question for you. What's the future plans for EcoStress, its scheduled plans, and being done with ISS pretty soon, and then what are the future outlook for flying as an independent instrument?
Yep, so EcoStress was originally supposed to be a one-year mission and has been extended multiple times. So now we've been flying for 4 years. We have a spot on the ISS until at least September of 2023, and we may be extended beyond that. That will depend on ISS availability, the availability of our slot. Beyond that, we're working on EOS, which includes a mission that will map the Earth's surface, biology and geology. That's SBG. And that will include something that looks very much like EcoStress, but it'll also contain midwave channels with high saturation points specifically for wildfire and volcanic eruptions. And so that will be launching in about the 2027 timeframe. And it'll be a polar orbiter, so fixed time revisit. But we have been collaborating with ESA, CNES, and ISRO, who are also launching thermal instruments in the next few years, with the idea that we could have daily revisit with pixels up to 60-meter resolution for the monitoring of wildfires and other hazards. So exciting times coming in.
Good, thank you very much for that.
Yeah, that was great. Thank you, Carrie. We'll go ahead and move on to the next speaker. And if you want to monitor the chat there to see if there's any follow-up questions. We now have Sujay Kumar, who's going to talk about the Earth Information System freshwater, and I believe there's some water fire connections in there as well. So can we get a sound check, Sujay?
Yeah, can you hear me?
Yes, perfectly. Thank you. So I'll come back on with my camera when you have 2 minutes left.
Okay, thank you. Thank you, Everett, for giving us the opportunity to present in front of this group. So I'm going to talk about EIS, or Earth Information System, which is relatively a new activity. The concept is sort of presented here. The idea is to look at the water cycle by integrating all of NASA's remote sensing and modeling assets simultaneously, and then showcase the capability to quantify the water cycle components and address some of the grand challenge problems in hydrology. So within the freshwater team, we have a specific focus area to examine the connections between fires and hydrology. So obviously that requires no real explanation to this group, so I will go straight into that topic. If you can go to the next slide. Yeah, some of the high-level objectives are shown here in this schematic and described here. So the basic idea of this effort is to look at the fire and hydrology connections, both from a pre-fire as well as a post-fire perspective. Obviously, hydrology and particularly the dry conditions have a significant influence on the fire development. And then after the fires, there is obviously big impacts on ecosystem as well as changes in the hydrological response. So our attempt here is to look at this and study these changes in the last several decades using a large set of remote sensing and modeling assets. And we also want to look at some possible feedbacks that could be happening here. For example, these drier conditions that promote fires, they essentially, after the fires, lead to more open landscapes. And with fundamental changes to the land surface hydrological response regime in terms of how water budget gets partitioned into ET and runoff, and that could lead to more sustained land degradation and more chances of fires happening. So if you can go to the next slide. So these are some prior studies, more recent ones that kind of have led to this particular project and the focus. This is the Australia 2019-2020 fires, which I assume most of you are aware of it. So the top line shows the imagery from BIAS, and at the bottom line shows the vegetation optical depth anomalies from the SMAP mission. Although SMAP is primarily designed for soil moisture, it also outputs the vegetation optical depth, which is an analog of vegetation density. So again, the key thing to focus here is the 2022 year, the 2020 Australian summer period, when you see these large negative anomalies in vegetation, which was a combination of the significant drought and the flood happened and the fires that happened. If you click once, so in this study, we looked at the subsequent impact on water cycle after the fires. The two panels show here on the right changes in evapotranspiration and the runoff after the fires. So once the vegetation is taken out, there's a lot less ET and a lot more runoff, which was captured by assimilating and including all these products. And sure enough, in New South Wales and Sydney, in late that year after the fires, there was a big flood event that happened. So again, we think some of this fire-based vegetation disturbance had a big influence in what happened here. If you go to the next slide, there's another case study that we did recently over the Brazilian Pantanal. So on the left, again, you see the map of the domain. This area is, there's a lot of grazing and controlled fires in this area because this area is a lot used for grazing and cattle ranching. So the top left panel shows the grazing activities and places where typically the grazing areas, the cattle ranching is low, is shown in red areas. And the bottom row shows the areas where fires happened, the panel C. And curiously, the interesting pattern was that most of the fires happened in areas where there was traditionally less cattle grazing. So what this points to is the fact that there was intentional fires likely to expand the area of grazing. So if you click once, we also looked at the longer term record to see how fires have happened in this area and how the ecosystem and the hydrological responded. So overall, except in the last 2020, 2019 time period, the ecosystem was pretty resilient to droughts in this area, and vegetation recovered fairly quickly, except last year. And similar to the Australian case, we also saw a big change to the hydrological response, with that regime shifting to more of a runoff dominated regime in response to rainfall. So this has obviously big consequences, not just from a flooding perspective, but also from an ecosystem sustenance perspective. This area, as you may know, hosts one of the world's largest biodiversity. So having that change to the hydrology may have fundamental impacts on what happens to the species and the plants there. The next slide. So switching gears, and so this kind of motivated what we are doing in the EIS project. Right now, we have just about finished with a scoping time period where the idea was to identify some domains to study this historical association between hydrology and fire. And then right now we are in the phase of setting up model runs and domains. And the idea of talking to you all is to see if we can find some science collaborators for this activity, and so that we can get some advice on the actual fire side of the cases, and possibly look for extending this for real-time application down the line. Next slide. I'll skip this slide for the time being and go to the next one, which sort of showcases the two domains that we are focused on. One is over the Western US that covers California, Colombia, Sacramento, and San Joaquin watersheds. This area has shown to have a lot of fire events in the past, and we have a lot of data sets, remote sensing data set, including the eco-stress data that we just, that can be used to, again, evaluate the hydrological response in terms of how the ET recovers and the vegetation recovers. And the other domain we are focused on is over the Amazon, where, again, we have a bunch of studies that show the significant impact of the human hand in fire development and the changes after that. Next slide. So I want to also point out that there is actually a separate EIS fire team who is a bit more focused on the fire monitoring aspects. And this is led by Doug Morton at Goddard. And some of the key tasks are described here, where the idea is to, again, focus on active fire monitoring and look at fire weather conditions that promote those development, and use remote sensing to map out fire areas and emissions and so on. So there are tasks focused on fire spread and monitoring. So our role here is to provide some of the hydrological contributions that or hydrological data products that help with this task. Next slide. So within the fire hydrology studies, this is a list of all the observational products and model setup, just for your information. So again, like I said at the beginning, we are using a large number of remote sensing products, starting with precipitation, ET, terrestrial water storage, vegetation water content, estimates of ET, primarily from the Open ET effort, and estimates of river flow conditions. And so we are running these at a 1 kilometer spatial resolution, excuse me, by assimilating all these data products within a land and hydrology model, which helps to incorporate both hydrological conditions in terms of the moisture changes, as well as the vegetation disturbance that follows. Next slide. So this is a bit more detail on the Western US domain here. If you go to the next slide, this showcases where we are. This is a fairly large domain from a model setup. We have conducted some model-only simulations, and we are in the process of assimilating all those products that I just just described. Next slide. So some preliminary analysis, again, looking at that feedback cycle that we saw. This is an example of what the remote sensing information gives you in terms of providing assessment of the pre-fire conditions. So there's a time series that shows the changes in or the anomalies in terrestrial water storage. The model only is shown in the blue line, which doesn't seem to have it seems to be fairly flat, whereas the TWS anomalies from gray shows a decline in the terrestrial water storage. So essentially, there is a huge groundwater pumping signal in this area that that leads to that change, which is not captured by the model, and assimilating that product, the GRACE product, is essential to capturing those dry soil moisture conditions. Next slide. Another example with ET from the OpenET product. The top row shows a model called DysAlexi, which is using a thermal IR-based information for developing ET. And then at the bottom, you can see the burned areas from MODIS. So they have a very nice correspondence between the two, essentially. So the idea is to use products like DysAlexi to examine the ET recovery, which is an example shown in the next slide. Over 3 different areas with the different levels of fire intensity. The R2 region is the region with no fire, and the time series shows the time series of ET from DysAlexi. So there's little interannual variability in the ET signal in the R2 domain, whereas over the fire domains, you can see a significant difference. And we also computed a recovery metric, which is shown in this F bar plot, which shows how the different domains respond differently based on the severity of fire. So some of these things, these are basically examples of how we can characterize the fire severity and recovery and its impact on ET. Next slide. And this is another example of looking at MODIS leaf area index. Again, that shows the vegetation recovery aspect of the fire. So again, from our analysis, it looks like the 2018 fires was a bit more severe, whereas the 2019 fires barely had an impact on the vegetation side. And the anomalies persist for a longer time, which obviously has an impact on the hydrological response. Next slide. So this is again a quick look at the South American domain that we are doing. The idea is to cover an area that has had a lot of land use changes as well as fire activity. Go to the next slide. Again, this shows a preliminary analysis of the land use changes in this area. And the MCD12Q, which is basically the land cover change over the last couple of decades, is plotted here, and that most of the areas with forest loss is nicely sort of correlated with areas where there's a lot of significant fire activity. So, and then the bottom row shows the changes in land cover because of these fires, which shows a decrease from forest and sort of an increase in the savannization, which is documented in the literature very well. So the idea is to incorporate these products and to examine the changes in the hydrological response. Next slide. I think that's sort of the end here. So that was sort of a quick run through of what we are doing in the EIS freshwater project, which is, again, it's not really focused on the near real-time quantification, but we are looking at the science level, the connection between fire and hydrology as it relates to both pre-fire and post-fire conditions. So here we are looking for science collaborators to co-develop and advise on these case studies. And like I said at the beginning, explore possibilities for routine use of some of these capabilities down the line. I'll stop there and I'll be happy to take any questions if there's time.
Over to you, Vince.
Yeah, I don't see any questions coming through on the chat. Yeah, nothing really. Just a note. Dale Hamilton, your camera's on, and we suggest you turn it off. Save bandwidth issues for us. Thanks. Yeah, so Jay, I don't see any questions coming through on the chat, but stay tuned into the chat in case we do have any further questions come up regarding the collaboration issues that you spoke to. With
Thanks,
that,
Rick.
I think we'll switch over to the next speaker. We're doing pretty good on timing for everything. We're back kind of on schedule. And so our next presenter is Gilberto De Salvo. I hope I pronounced that right rather than Gilberto. Speaking on wildfire AI, fast detection and visual confirmation from anywhere. And Gilberto, I'll let you take it away. Let's do a sound check for you first and make sure that we can hear your.
Thank you, Vince. Can you hear me?
Yeah, coming in pretty good. Maybe a little soft.
How about now? Is that better?
Yeah, perfect. Great.
There you go.
Let you take it. You've got the next 15 minutes. Thank you.
Thank you so much. And I'd like to thank TFRSAC for the opportunity to present our work today. Again, I'm Gilberto De Salvo, and I'm the CEO of Delfire. We're a phase 1 SBIR team supported by the DOE Office of Electricity to develop an early wildfire detection approach for grid-related fires. I also live in Pasadena, and I look forward to hopefully meeting many of you at the IAWS conference next week. It sounds like it's going to have pretty good attendance. We're leveraging a ground-based field-installed AI to detect fires rapidly, and we're using multiple overlapping sensors to increase confidence. And since no AI is perfect, it's my belief that sending a small picture back from confirmation is still best. Next slide, please. I was thinking about an opening slide on Monday, and this popped up in my news feed of the New York Times. Hopefully that's not advertising AI doing its best job, but I'll take it. This study by First Street Foundation shows the risk projection over the next 30 years. And what caught my eye on this one was that it accounts for a significant curb in greenhouse gas emissions taking place over the next 30 years. So this is maybe the best case scenario that we can hope for. Next slide, please. And we're particularly focused on the utility market, and with a aging infrastructure, we think that there's going to be quite an increasing number of fires being either attributed or caused by the grid over the coming years. And this is where rapid fire detection could lower some of the damages from these fires. Next slide, please. Over the last year, we've developed a smart multi-sensor device prototype, which can, at fairly high confidence sensitivity, through correlating multiple different AIs, detect fires through a few different sensors that I'll talk about next. Once there's a detection, the data can be pushed back to a server in a matter of seconds and relayed to a web portal where it can be viewed by the user or push notified by email. At the same time, non-critical data can be stored on the device and sent back whenever the user wants to access it in the future. Next slide. So as I mentioned, we're using a visual camera to detect flames or smoke in the field of view. Detection distance here will vary based on conditions, but I think we can probably operate at a range of 3 to 5 miles on a clear day from a height of about 21 feet. Lower range detection can be achieved by an infrared camera also on board, and there's 2 opposing cameras to monitor along the power line. If close enough, we could even detect hotspots on the conductor itself to maybe prevent some fires. There are 2 benefits to working from this perspective. One, that we can work day or night, and the second one that we can probably detect during fog as well using our thermal camera. We also have an onboard smart sensor that can detect nearby fires by essentially smelling them, or detect fires outside the field of view. Overall, we think that this multi-pronged strategy will help lower false positive and false negative detections while leaving the decision-making in the hands of a human. We also provide a series of other sensors that can inform both risk modeling and where the fire is likely to go. Next slide, please. So as I mentioned, our goal is to report ignitions faster and start mapping some of the root cause analysis of what is causing some of these fires along the grid. By constantly monitoring the area, we're able to hopefully capture the data that led up to a fire and start mapping the underlying causes and maybe even look for them in the future and prevent them. As I also mentioned, by the perspective that we're using, we can catch fires day or night, or even when there's cloud cover that may confuse other models above the working from above a mountaintop. Since our AI is running directly in the field, we're also low power and low data, meaning we can operate anywhere, including low connectivity environments. Next slide. And actually, sorry, one more. As I mentioned, a lot of these mountaintop cameras tend to catch fires fairly late once there's a significant plume of smoke. Next slide. And so we'd like to open up a new space of detection in the ultra early space, as well as capturing, like I said, all that information that is around the fire. On top of that, we also enable remote inspections. So nearby foliage can be observed occasionally rather than every couple of years along the power lines. Out-of-phase detection measurements can be visually confirmed if there is an issue without having to send a crew out, or hotspots on the line can be observed in near real time. Wind vectors can also be measured from near the power line itself and only reported back once a gust is exceeding a set value, for example. Next slide. So this is what our device looks like today, our prototype. And essentially, we're looking to offer multiple data access mechanisms and support different stakeholder applications. We don't want to set how our data gets used, both in the emergency data and the background data that gets recorded, compressed, and then occasionally sent back to our servers. We're looking for new partners to either use our data or provide new input data that we could leverage both on our servers or on the modeling. Next slide. We've developed a basic data access portal for accessing both the emergency data and the non-emergency data. Here I'm just showing you wind vectors captured at a location over a period of time. On the left, you have the direction of the wind, so you can see how often a wind is blowing in that line from a certain angle. And on the right, you have the wind speed mapped out for that. The data can be downloaded locally directly from the portal or accessed through our API on a user-specific application. Next slide. Just wanted to run through quickly the different types of sensors that we have on board. We provide geolocation, fire alert based on a couple different AI models, wind data, wind speed, wind direction, temperature, humidity, VOC, CO2 measurement, visible images and infrared images in both directions. And we're able to support fairly easily additional sensors, including air quality monitoring and a few other ones that we've already tested. And we'd love to get suggestions for additional sensors that either would improve our platform or that you think would be helpful in terms of both pre-incipient steps, the early detection of fires, and or risk mapping. Next slide. So I'd like to also show some work done by Peter Melitz at NASA Ames. We've been collaborating with them to try and showcase how our data can be used in other applications. They've built Odin Fire, which is a framework to build fire-specific applications that can run inside a stakeholder premises. So this could be put into a forward command post and essentially run there locally to integrate multiple different input sources and easily make them accessible for the stakeholder. The overall goal is to quickly detect threats, rule out false signals, and manage resources. Think of something that's basically managing a planned evacuation. Next slide. This is a quick demo that we've made. On the bottom left, you can see a unit which is turning from a non-detection to a detection. and the picture which is sent back here in a demo can be basically accessed by the user in a couple of seconds. And what we're working towards now is actually showing the geolocation of fire relative to the unit, so they can be mapped out and using combination with our other data to provide risk modeling. Next slide. So this allows to do visual confirmation of a fire. Let's say there is a false negative because you have strong cloud cover overhead, or you know, you don't have a detection yet at that site. We'd be able to pick up the fire in a matter of minutes and basically showcase a picture within a minute to the end user for confirmation. On the right, you have a false positive, which is a trash incinerator in downtown San Francisco. And this is almost a constant hotspot that comes and goes as they burn trash. There are actually quite a few of these around the area. And so a nearby sensor could essentially act as a control to see whether there's a real fire nearby or whether this is a hotspot being detected by another normal use of an incinerator in this case. So it allows the user to quickly, in a matter of seconds, parse false positive and false negatives, as well as enabling some human interpretation of the maybe underlying root cause of that detection. And this is the contact info for Peter up at NASA Ames. And what we're looking for here is if anybody has got some timescale infrared data, we would love to collaborate on maybe showcasing what can be done with early detection and creating a small demo of the power that can be brought together by local ground-based as well as satellite-based infrared detection. Next slide. Here I want to showcase something else that we're working towards. We want to use our data source through the Odin server to essentially inform some real-time or near real-time model predictions of the fire behavior. This has been done by Willow Labs that we're collaborating with. And 5 minutes is a worst case scenario estimate. It's more likely to be in a matter of seconds for a small fire, but 5 minutes is for a larger fire that covers a fairly significant portion of the area. Next slide. And the idea is to have our data source in under a minute and being pushed to the server and then informing these models so that you can plan evacuations accordingly and in real-time display, near real-time display how the fire is likely to move and how it's likely to spread with different confidence intervals in the area. So next slide. So I'd like to thank our team and advisors that have been incredible help over the last year. And I'd like to invite you to reach out to both strike collaborations, and we're looking for, again, any infrared data, and also if anybody has the ability to get us on the ground at a prescribed burn, we'd love to do some real testing on the AI models that we developed. Thank you, and I'd love any questions.
Thanks, Gilberto. I got a real quick question for you. Again, this was funded under an SBIR by, is that Department of Energy? Is that correct?
Correct.
Cool. We've got back-to-back SBIR presentations. The next one coming up is also an SBIR, I believe, through the Forest Service. There is a question in the chat from Haiyang. Gilberto, what kind of IR camera are you using? And then also, can you talk more on the details of your AI algorithm? Is it a kind of neural network-based classification or data fusion?
It's both. So we're running a neural net, two different types of neural networks actually, and then we're so depending on the type of detection that we're getting or the sensor which is detecting an issue, we're running different types of models. That's a short answer. On the thermal camera that we're using, it's for now a fairly low resolution FLIR camera. It's about 160 by 120 pixels, which I think will give us a reasonable detection range of about half a mile on the infrared camera. we're working on upgrading that under hopefully a phase 2 effort in the coming months.
Good. And there's one other question here from Mike Seablum. Is there any linkage of the data to CAL FIRE FireGuard?
Not currently, but would love to collaborate. And I think, the type of data that we're going to produce, as well as the alerts, will work very well with CAL FIRE's 15-minute aerial response time.
And a suggestion for myself at NASA Ames, you might also look into any type of potential collaboration with, I believe it's EPRI, the Electrical Power Research Institute in Palo Alto.
I will. Thank you so much.
Good, thank you. I see we've got another question. I'll leave you to answer that in the chat, as we'll try to get back on a little bit of a schedule. I know we have some slop time into the open break session, but with that, I'll let you answer that question in the chat. It's from Bill Beverly. So with that, I'll start on the next presentation, and that is going to be by Steve Pollard. And Steve is going to be talking from his company Trident Sensing on the TFRSAC Tactical Fire Remote Sensor Phase 1 results. And as I mentioned, this was an SBIR, I believe through the USDA / Forest Service program efforts. So take it away, Steve. Let me do a sound check with you and make sure you're all ready.
Sound check, Vince.
You're good. All
Okay.
right, ready to go.
Sorry, there's some F-35s flying over the top. We're located at the Ogden-Hinckley Airport, about a half-mile south of the NIROPS crew, and we're right under the initial for Hill Air Force Base and their F-35s. Anyways, I'd like to thank USDA, Forest Service, and NEFA. SBIR process is really good. It comes in the way of a grant for all you small companies out there. It's not a contract. It doesn't have as many burdens as some of the other ones. I've gone through Department of Defense SBIRs, and typically that's invoicing. It's a contract. Here it comes in a form of a grant, so it's a lot easier for a small company to make good use of the funds. So a shout out for that. Next slide. All right, I'm going to give you an overview of the overall TACFIRE's concept, talk some about what we were able to do for a phase 1 concept demonstrator. This was not a paper study. This was actually go out and fly hardware and get quantitative results. We also got some qualitative results over a prescribed burn. A little bit about the origins. I joined this group. Everybody's got a story. My story started August 2016 with a fire near my house up near Oakley, Utah. So that's how I got trained in the vortex of TFRSAC. Next slide. All right, so here's the concept overview. We felt like there's room for technology convergence, much like the smartphone. Took a bunch of miniaturized components, packaged them up in an innovative way to use those components differently. We thought we could do the same for tactical fire mapping. So we got miniature sensors now, really good miniature INSs. You'll see how well this performed. And then compact computing is just ubiquitous. So packaging this together with innovative software, we get something that's strapped down, so no moving parts, no sensor console, wingtip to wingtip coverage, direct to map products, no intermediary imagery interpretation, and then simplified airworthiness through the 337 process instead of an STC, which is required for a full motion FLIR ball. So you can actually see how small this sensor is under the wing of 2 different aircraft there. Next slide. So the goal is to get a tactical fire mapping sensor on everything that's flying over the fire. So completely different approach than more expensive dedicated platforms. It's make everybody a sensor node. All the way from small UAS up to the largest aircraft out there. Next slide. All right, if you're going to put all these sensors, we're talking hundreds potentially of active sensors flying on a day-to-day basis. You've got to do your map processing differently. As I said, there's no intermediary imagery interpretation. You've got multiple aircraft flying, overlapping. You've got strategic sensors. So we decided kind of on our own that we were going to take the 1/3 arcsecond USGS database, the digital elevation model that gives you a 8x10 elevation pixel of the Earth here in CONUS. A shout out to Burjit, who has joined the team. So this is using a USGS product that you're contributing to this fire mapping already. We wanted to animate the fire map like a weather radar so you can see the trend information. Everybody knows how a weather radar works. They can interpret it very easily. And we wanted to be able to weight all the sensors out there and express the best data and not throw anything away. So that's kind of the concept there. And I'll show you later, but this results in a very, very skinny segment of map data. Next slide. All right, there's our TAC fire sensor, 3 microbolometers, 2 wide field of view, 1 narrow field of view. That's the green one that's diagonal is the narrow field of view. These have f1.0 lenses. There's no operator station other than on-off switch and a couple of lights that flash to tell you whether it's working or not. We did post-processing for phase 1 and are headed to real-time processing in phase 2. Next slide. All right, Vince, if you could press the button there to make the video work and just keep mashing it, please, just to keep looping it. So here you kind of see those 3 different cameras color coded, red down, blue left oblique. The green one is the narrow field of view. And the little yellow dot is the actual aircraft path there. So we're assembling hundreds and hundreds of images. And in fact, this is 99.5 million temperature observations to get the map data that's on the right, that's just registered to the 1/3 arcsecond wireframe. Next slide. So we did quantitative testing with thermal targets. We thought it was real important, phase 1, to see, hey, does this really work? And we also did some qualitative over prescribed burn. The previous guest, I'm happy to talk about that process if anybody wants to know what we did there. We also looked at other qualitative things, sun reflections, retro reflections, maneuvering. We didn't have any issues there. I'm not going to talk about those specifically. Next slide. So we borrowed 3 targets from CAS up at the NIFC and made 2 more larger targets. These are charcoal briquette targets. They have to be tended. You have to knock off the ash when you do this. You can see we mounted this on our vintage 52 Beechcraft Bonanza, and that little dot there, that's the actual sensor that's producing all of these results. And there's our motley crew there. It's actually a fair amount of effort to get a good test off. We encountered weather and availability of people, ran out of charcoal. So it's a little harder than we thought, but we accomplished it. Next slide. So the first place we went was level terrain. This is 3 passes. That's what those 3 plots are, 500,000, 2,000 foot. The red boxes are the actual targets, the smallest at the bottom to the largest at the top. So just about 50 times difference in the sizes as you go from the little 0.02 meter to the 1 meter squared. The X's are the actual pixel hits. Out to. So we're real happy we're able to demonstrate with these tiny little cameras the 6 to 10% sub-pixel hotspot detection. 6% is kind of the generally accepted point where false positives become unacceptable. So these little cameras with their little shutters and NUCs work very well. And then we demonstrated right around 10 meter end-to-end accuracy. So this is all the errors in there, including there's about 20 feet of altitude error here. You can only measure position to within 2 to 3 meters. So we felt this was really good. Of note, we had a cloud deck and couldn't go above about 2,000 on this day of testing. Next slide. Then we packaged all that up. We took it to a mountainous terrain. This happens to be my neighborhood, representative of the wildland urban interface. And it gave us a chance to look at a more complex elevation model, as well as to put a target underneath vegetation. One of our objectives was to see whether we could, with all these framing points of view, whether we could do a better job of looking under the canopy. Next slide. So top right there, target 3 was put underneath conifer trees, pretty dense overview. We actually picked that target up. And target 5 in the lower right, that was untended. We lost a target person, and so we never saw that one. These things have to be tended, and you have to keep on feeding the charcoal on them. Next slide. Here's a representative 2,000-foot pass, much wider spread, over 1,000 meters apart. That top target, number 5, we never saw it at all because it was untended. Here we saw targets 3 and 4. 3 was underneath the trees, so we picked that out, which was one of the objectives, to see whether we could do that. And the end result was no degradation of the subpixel detection or the georeferencing here. It's still got in the around 10-meter range. Next slide. We did 4,000-foot pass here with similar results. We got a little wider geolocation, and we got a little bit of false positive off the snow. So turns out snow, as you saw on the target slide previously, it turns out it's a very good reflector of IR energy, probably similar to some rocks that are out there. Next slide. We went down to Show Low, Arizona. A shout out to Weiler Heffingler in the Apache Sitgraves National Forest. I connected with him, just cold calling, and he was able to provide the time and location of a burn, prescribed burn. We were able to get over from the light off through the first 4 hours of it. We were able to fly multiple maneuvers, simulating tanker missions, orbiting aircraft, S-turns. We did a lot of different things here in the qualitative stage. Great thing about this is you get rapid fire progression because they're actively lighting it, and there's no TFR over the top of prescribed burns unless they get out of hand and become a real fire. Next slide. So here's some slides of that. The top is just some progressions slides. Bottom left, an idea of what the fire actually looked like. The early stuff was actually burning out by then. The bottom middle, just by chance, Landsat 8 went right over the top. That's like a once a week type thing. So I don't know if luck was with us. And on the bottom right is the MODIS and VIIRS. You can see MODIS didn't do too well in the geolocation. VIIRS did a pretty good job. They were latent by about 2.5 and 3 hours each in terms of picking up the fire. Next slide. So here's a little bit of qualitative stuff right at burnout. You can see when they just started lighting, the sensor did real well at georeferencing that. And then as they lit along Highway Road 135 there, that was their fire break. You can see the sensor did a really nice job of containing the fire on the proper side of that, which was one of our key metrics when we picked that 1/3 arcsecond wireframe, was to be able to figure out which side of the fire break is burning. So that worked out really well. Next one. Let's skip this one, Vince, and go to the next one. That's just some more qualitative stuff. High altitude. This is the only actual image you're going to see out of me because we typically don't try to look at the images, but I just wanted to show you all the way to 9,200 feet. The narrow field of view was providing great data. The wide field of view is picking up the big bulk fire stuff. So this sensor will work all the way up to probably pretty close to where NIROPS is flying. Next slide. This is probably the most interesting part about it. This is actually the first animation I showed you. We have 432 images, almost 40 megabytes of data. By the time we compress this down and do the map processing on it, we're at 54 kilobytes of data. This is now something that can easily be shipped around via narrowband SATCOM, Wi-Fi base for a tanker base to download when they get back. So I think this is a key enabler of trying to get this real-time data around and into the hands of people. It becomes really skinny. We're not looking at images. Next one. Go ahead and click this one, Vince. This is just 4 hours of imagery. It's starting, you can just see it starting in the lower side there. And this is catching the propagation of the fire as it goes. And you'll see at the end, some of the original stuff is starting to age to gray as it's going out. All right, so that was showing the key objective of animating the fire map. There's lots of work we can do here. We put encoding intensity and other things on this moving fire map. Next slide. We did integrate mechanically, electrically to a small UAS, but it was winter, and we're a little worried about the federal rules on flying anything with the Chinese components. So we tabled this to IRAD, and we're going to do that this summer. But the swap was very compatible with the small UAS. It'll get better with the phase 2 sensor, which will separate. So we achieved all our phase 1 results, demonstrated the feasibility. Phase 2, we're headed to real-time map processing. We budgeted for a beyond line of sight transmission capability. We're going to centrally aggregate map data and then push it out. And we're interested in collaborating on the data formats, but push it out via web to get it into users' hands, and probably a little better geolocation accuracy. Lots of areas for collaboration here. You can kind of think of like this as a mini satellite flying on a wing or on a belly. And so there are other sensors that can go in this. We already have the time, space, position processing. So particulates, wind, other things. We could capture where we're striping the retardant and the parameters of the release that could be done for post-retardant, basically checking the effectiveness of the firefighting mission. Some opportunities for machine learning for hotspot, reduce the false positives. Combining time-based observations with predictive models. And the toughest nut to crack, because it's hard to pin down the pilots, is what would they like to see out of this in the cockpit in terms of would it help them with any situational awareness in their job? All right, so that's all I have, Vince.
Great, thanks, Steve. Great presentation. Really enjoyed the advances you made in the last year with the SBIR. I've got a quick question for you, and then we'll take one from the chat, which should be easy for you to answer. What are your power requirements, or what do you use for power for your units?
You know, an amp or so of 14, 28 volt.
Okay,
maybe 2
cool.
amps when we do the real-time processing.
Okay, so when you're mounted on a wing, where do you get your power derived from?
We'll wire power to the wing station. There could be a future turbine, wind turbine type of thing if it needed to be self-powered.
Okay, yeah, that's what I was curious about. On the chat, we've got one question. I think you answered it in your summary slides. Ed Freeborn asked, does TACFI include a real-time comms link? And if so, what are you using? So I think that's identified as your phase 2 options, but
yeah, that's phase 2. We're going to go to that. We're going to do the onboard processing and ship the data off and demonstrate that. We settled on Iridium Certus. I noticed Tom Mellon mentioned that they're doing in Marsat. I assume they're a Swift broadband modem service probably for the new NIROPS aircraft. So maybe we can collaborate and see how those two work in terms of shipping map data.
Everett just pointed out to me in the chat that Scott Kaplan's got a question above. we could handle it offline. So just see if you can grab that question from Scott Kaplan at 10:58 or my time.
I see
10:50.
that one. Thank you.
Okay, thanks. Thanks, Steve. Appreciate it again. It's nice to get report outs from you on the SBIR and all the SBIR programs. We really like to see those innovative new small technology development companies really start to make a play in this game, and we appreciate the sharing of information from groups like yourself and others. With that, we'll move on to the next talk, an AI-enabled airborne imaging deriving smart solutions presentation by Greg Davis. Really, it's a talk about Overwatch, update on the autonomous mapping program. So with that, I'll turn it over to Greg. Greg, you want to do a quick sound check and then start in?
Great. Yeah. Thank you, Vince and Everett. Can you hear me okay?
Sounds good. You're free to go.
Okay, great. I'll try to get us back onto schedule here. So I'll start with just a quick introduction to Overwatch imaging and what we do. I think you'll note many similarities to our previous speaker and pretty, similar trends to a lot of the themes that have been addressed by many of the speakers in this conference. So as always, Vince and Everett and Bridget, thank you for arranging a great lineup of speakers today. Next one, please. Okay, so Overwatch imaging, we're providing intelligence solutions to agencies around the world. We've specifically been supporting the U.S. Forest Service with nightly fire mapping missions and fire detection missions since 2018, providing daily and nightly support in Australia and Europe as well. So as our last speaker was saying, we love the idea of let's get sensors over every fire. We're based in beautiful Hood River, Oregon. We'd love to see anyone out this way. Next one, please. Okay, so you'll have to click through a few times here, but our mission is AI-enabled sensor technology that provides refined information to support time-critical missions. We support search and rescue applications. We support some defense applications. We support some utility applications. But our first love, and as reflected in our team makeup here, as reflected in kind of the passion of the team and family members working in the field, is supporting the wildland fire mission. So when minutes matter, we are working to provide the right information at the right time, and doing that in a way that is easy by the use of smart software technology and artificial intelligence techniques. Next one, please. Great. So I mentioned we've been providing our capabilities continuously in the field for a number of years now. You can see a list of different customers across the top here. One piece that I think is exciting about what we're doing, and hopefully aligned with some of the other speakers in the conference here, enables this technology to get out there and collect more data in more places. We are able to put our technology into lots of different aircraft types, from drone technology through big high altitude fixed wings. So 2021 was an exciting year for us. Thanks to Tom Mellon for some of the statistics here. We are proud to have provided the sensor technology for 85% of the NIROPS maps last year, and just seeing the team departing our office to start our NIROPS operations tomorrow for the 2022 season. So more than 5,000 hours and nearly 3,000 different fires supported or fire maps generated across 300 million acres of land mapped. We're using this experience to continuously improve the technology to make sure that we're delivering relevant information at the right time to the right people at the right time. Next one, please. Thank you. So our approach to doing that, we're making imaging systems that are purpose-built for the applications and the aircraft that we support, and then collaborating with users and viewers of that data to make sure that we are providing the information in different ways, different modalities, collecting the feedback from those users, incorporating that feedback into a continuously improving software product, and trying, at every turn with all of our different installations around the world to incorporate agency and end user feedback and make sure that we're fitting into the workflow and getting the right data to end users in the way that they need to see it. Next one, please. Okay, so that completes our sort of who Overwatch is and what we're doing. If you could flip to the next chart, please. So a focus on near real-time data in this conference. I appreciate that focus. That's our favorite way of how are we going to help make this wildland fire situation better. So why is near real-time data important? We'll talk about that in a couple different ways in the next couple charts. So let's go to the next one on rapid response and decision making. When we have more real-time data, we can use that data to support rapid response and rapid decision making, as long as, or provided that, the data is getting to the right users. So we love seeing the various technologies supported and presented over the past couple days, where imagery from lots of different sources, including our sensors and including those of the various agencies, is pulling, is feeding this geospatial repository and quickly getting that data to support decision making, which drives safety. So we know that data alone can't be the answer. We need the analytics to cut through the noise so that we are both seeing and telling to make sure that we are improving safety through rapid response and better decision making. So that next chart on why near real-time data is important, it reduces risk to personnel. So we've heard a lot of focus over the past few years on the tracking of personnel on the ground. We've been working on with agency partners on new fire detections with fire movement. So the more we can drive situational awareness, that allows us to, or allows the community to, detect problems early. The more critical observers we have, the faster and the better we can protect those teams on the ground, make sure that that escape routes are maintained, safety zones are maintained, and make sure that we're doing our best to keep the crews on the ground as safe as possible. So then next one, please. So a third good reason why near real-time data is important, it provides a common operating picture that enables and drives multi-agency cooperation. So we're excited and proud to be collaborating with several different US federal level and state level agencies and feeding a common geospatial repository such that lots of agencies can work together and collaborate and all feed our best ideas. And that is supported when we all have access to a rich common operating picture. So the more data we can feed into that common operating picture, the more that each of these agencies can understand and apply their best ideas to improve the future. Okay, next one, please. So our conclusion here then, if data is good, then more data is better. So we love the ideas reflected throughout the talks of the past couple of days. Let's continue to drive more ways to collect more data, and then we can reduce the noise from that data and provide those insights that drive rapid response, that drive safety, that drive multi-agency collaboration around a common operating picture. So the more we have data, the better we can do to improve the outcomes. So some ideas that I'll throw out, and nothing is easy here. We all know that, but some ideas that we could pursue as a community to get more data into the geospatial repository. So there are lots of exclusive use aircraft across the various federal and state agencies that are involved in aerial firefighting. All of those aircraft could carry data collection sensors that are feeding data into this common operating picture. Technology like ours and like some of the other companies here have presented are able to reduce that data to cut through the noise. So, the time has come that we can collect data from all of these aircraft that are supporting fire suppression activities, fire spotting activities, lead plane activities. There's lots of aircraft involved. All of those can be imagery collection nodes, data collection nodes. Next idea, let's develop partnerships with airlines and all the other things that are flying over fires. So every time any aircraft is passing overhead, we can update a shared common operating picture and drive better response and better safety for our teams on the ground. And then finally, we can process data other than near real-time imagery and fuse that information with the image data that all these sensors are collecting to improve the overall situational awareness. So this can pull into play ground-based sensors, critical infrastructure maps, lots of different sources of information to continue feeding better operating picture, better situational awareness, leading to better decisions faster. There's my update. You can flip to the next. Thank you, Vince and Everett and Birgit for the opportunity to speak today, and would love to hear if there's any questions. Would love to follow up with anyone.
Great, thanks, Greg. I'm looking to see if there's any questions. Appreciate the update too, by the way, from Overwatch and your capabilities and your contracting efforts with the partner agencies. Let's see. I don't see any questions. Maybe some will pop up during this break session or the discussion session that we're moving into right now before the break. Okay, let's see.
Hey, Vince.
Oh, yeah, go ahead, Everett.
Yeah, I just wanted to say, Greg, that I like some of your last couple slides there that talked about, the data is good, more data is better, and one of the things that I've been really leaning on is as we get more and more volume in our data streams is to figure out ways to better leverage those data streams without parking more analysts in front of screens, so trying to use artificial intelligence and machine learning to pick out the pieces that you need, doing data fusion so that if you have multiple systems that are looking at the same area, you can use that for cross validation to make sure that, to help bring down false alarms and so forth. So there's a number of things. I think, we're trending in those directions. A lot of the work that I see being done by the folks that attend these meetings, that we're trending in those directions. And so I'm really pleased to see that. So I just wanted to kind of throw that in there.
Yeah, thanks, Everett. Great. I mean, I think the technology is here today and ready to support that vision, this fire season. So let's do it.
Great. Since we're in an open discussion period, is Gilberto still on? I'd like to ask him a real quick question.
Let's see. I'm checking the list here, Vince.
Yeah, he might have his microphone off. So
I see him in the list still, so he's still plugged into the meeting, but
his mic might be off. All right, I'll save the question. I'll put it in the chat for him.
Okay, and I guess this is kind of a time where any of the previous speakers have a chance to to weigh in with any thoughts or questions from the audience for the speakers. Now is a good time. We kind of we like to program in some time here to have open discussions at meetings like this. There's been a lot of really good information exchange today. You know, yesterday we had a lot of the agency updates and sort of the focus on what is needed by the fire community to help in its efforts to evaluate technology, to adopt new technology and so forth. And you know, one of the things that I believe it was the eco stress presentation. I always get a little bit nervous about seeing a system like that that's plugged into the space station, because you know that it has some finite lease time on it. But at the same time, seeing the data that's coming off of that system is really encouraging in terms of how we may be able to use that while it does have its you know, while it's up there collecting data. So there's kind of a balance of thought there in my head in terms of how to use some of these systems that have a shorter dwell time, and maybe something will spin out of the EcoStress system there that will provide a longer term similar capability type system that's up there. Let's see, I'm checking to see if there's anything. There is a hand there. See if I can figure out it.
David Green.
Hi, David.
I just wanted to perhaps follow up on Greg's very last comment about let's get going this fire season, and perhaps even your comment there about eco-stress and some of the other things that perhaps are not going to be around forever. Is there something this fire season to this point that was made about there's lots of data, there's lots of things, we're still struggling with transition, but from those who talked today about some of their capabilities, is there something that we should really be trying to pilot or demonstrate this fire season? And if it's other sensors that maybe are not going to be around for a long time, like an eco-stress or something, then there's the idea of what would happen next might mean that we need to show a certain capability now. So I just wanted to open it up to see if someone has some tangible recommendations of things that we should come together on as TFRSAC and try to do this year.
I see Greg Davis has his hand up there.
Yeah, I mean, I have a strong opinion about this topic. Yeah, so we have been operationally supporting fire map generating aircraft for several years. So that technology is in use, it's kind of proven, the data flow is proven. There are a handful of dedicated fire mapping aircraft on exclusive use contracts, government owned aircraft or call when needed contracts. There are dozens or many more aircraft providing serving roles like air attack, lead planes, aerial supervision, suppression aircraft, spotting aircraft, any number of those aircraft that are on, many of them on annual call when needed contracts or annual exclusive use contracts where the requirements can be updated, on a relatively short timeline, could carry sensors that could, without any additional work on the crews on those aircraft, drive additional data into a shared common operating picture. So all of the ingredients to make that work are proven, are operationally, relevant today. We just need to go do it. So, that's I guess my call to action is like, there's 10 fire mapping aircraft flying around the West every night. There's 100 fire aviation aircraft flying around. Let's grow by an order of magnitude simply by collecting more data.
Yeah.
I just wanted to second a piece there with what Greg said and provide some tangibility to the application, if I might.
Sure, go ahead.
Yeah, so we've been flying with a system on our aircraft for 10 years that we call SLUR, side-looking infrared. And it's provided a very, very good situational awareness for the crews in the aircraft and downlinking it occasionally. But the value, I think, there is that what Greg's talking of is the ability to convey information to people, and perhaps it could be parsed, not as like moving material, but as fractionated imagery every so many seconds that can be delivered by, well, the Iridium system can do that slowly. But the mapping software that Overwatch has, I think, is adaptable to some other pieces than the downward looking, and might be able to provide very good perimeter updates with their AI technology. And that is a smaller data set that could be delivered frequently, and would not require significant crew attentiveness, so that the air attack mission could continue as it does, and whatever data is picked up would be easily deliverable without crew being tasked with that job.
I think that was Joey Mercer speaking, wasn't it?
This is Hart Drobish from Courtney.
Oh, Hart. Okay, I should have recognized your voice.
Anyway, I think I'm very supportive of what Greg's suggesting, in that the application with a more of a myriad of sensing systems available on aircraft already operating in such a manner that they don't task the crew or the mission with a specific need to do things. The challenge in the community has been that an air attack airplane with sensor systems will be asked to do other things, and air attack supervisors typically have not been happy about having to say, no, sorry, we can't do that. Oh, gee, this is really critical. No, I'm sorry, we can't do that. That's not part of our mission profile. So that's been the challenge. But in the past, I've been supportive of the concept that we're there. We ought to have a better view, and if we could share it, especially the AI capability with perimeter, it would be a fantastic boon to the fire community.
Yeah, that's a good point, Hart. And I wish that either Zach Holder or Sean Triplett were online. I don't think either one of them is on at the moment, but so that they could provide their perspective on that. But I'm up.
This is David again. So sorry to cut you off there, but I guess what I'm hearing is there's a lot of interest, there's a lot of capability, and what I'm wondering, and Everett, you can tell me if I'm like, this is totally possible, is there the viability that basically there's a number of people here with a number of capabilities that wouldn't kind of disrupt, mission profiles, but we could almost cobble together a TFRSAC experiment for this summer by, bringing communities together, and actually over the next few weeks, cobble together, I've got this, I've got that, I'm going to fly here, I fly here every day. You've got a place to downlink the data, you got somewhere else to stick it, and you can throw it in your model. Can we cobble together out of kind of existing parts without creating a whole new, program, this synthesis? Is there something there that this group could, and maybe you just need some, a little bit of resources to kind of convene and fill a few gaps with some timesheets or something, but that's what I'm asking.
Well, that's something, David, that I could certainly try to pull together some folks and do sort of an exploratory conversation to see what's possible with that. I noticed that Scott Kaplan has mentioned several times that about the Civil Air Patrol, and they commonly go out when there's been hurricanes and natural disasters. They go out and they fly areas and take imagery to support those after action events. And Scott notes that they can easily be tasked. But to the sort of the bigger picture that David is promoting here, I think that that's certainly worth having a conversation. So what we can do is we could pull together a call a week or two after this meeting, figure out who would like to be on that call to have that conversation, to pick over the pieces of what's possible, where there may be some issues or hang-ups, whether it's with contracting or whatever the case may be. I don't think that any one of us, I'm a remote sensing person, and I'm not in the fire and aviation stovepipe in the Forest Service, but I know this. I know of Courtney Aviation's efforts in the past to to equip some of the aircraft that are flying fires, and got some resistance. Let's see, Sean says we're working on an RFA. Let me pull that up again there. We're working on an RFA to evaluate how to use Civil Air Patrol this summer. Yeah, thanks for that, Sean. So
I think one of the difficulties we have in pulling together something this summer is the fact that for the same reason we have the TFRSACs in the fall, late fall, and early spring, is we can get the attention of the fire management community involved in this exchange of information and sharing of demonstrations and capabilities. During the fire season, which is basically almost year round now, it's hard to get anybody's attention to step outside their normal routine job of serving,
supporting the fires.
Yeah, supporting the fires during the summer.
Right.
I think we got to take that into consideration. In years past, we've done flight demonstrations many years ago, 2005, I think, Everett. We did flight and capabilities demonstration of sensor acquisition from small unmanned vehicle systems through an RFI process or a request to participate process with a number of 5 different UAV providers overflying and demonstrating their capabilities over prescribed fire in the early June timeframe. And I think that process is the way that you're thinking, David, is to demonstrate capabilities. Or
I think like what I heard was from Greg, perhaps, and the others, a little slightly different.
Okay.
Is I think before we were trying to test certain sensors and certain capabilities that hadn't matured. I think what was being suggested here is that certain things have matured, but we haven't done that kind of integration. We haven't brought them together. And so the idea was that there are things that are kind of up there, and there are things that are perhaps more opportunistic. And then what hasn't been done is to kind of take advantage of those opportunities and then bring it together. And that was why the thought, and maybe I misheard it, was that there were some things that could be done without, the big plan of a campaign, or a few things that could be done without potentially disruptions to the existing work.
Business flow. Yeah.
That's what I was trying to ask about.
Okay.
As distinct from, a big planning, campaign to test a bunch of new things.
Right. I wanted to call on Joey Mercer. He's had his hand up there for a while, and then Phil Balin after him.
His hand's getting tired, probably. So.
Great.
Thanks, Everett. Hi, Vince. David, I just wanted to maybe use this forum to suggest a different low-hanging fruit for earth science. A while back, I remember you mentioned the idea of one satellite asset sort of potentially detecting something early and then sending a message to like another nearby satellite so that that next satellite could sort of get its payload, so to speak, ready for staring at that same thing. And just this idea of kind of a little network of satellites talking to each other so that we don't have to wait for like that same one satellite to make its full pass to see stuff again. That seems like a pretty interesting low-hanging fruit for a demonstration. I don't know if that's anything at all related to the question you're asking about for something as early as the summer, but I've always thought that that was a really compelling idea that you brought up at that time.
Yeah, the sensor web, autonomous sensor sharing concept. Yeah.
And let's turn to Phil Balin.
Yeah, hi, Phil Balin here. David, and I'm interested in our one area that we're interested out here in California is that public health aspect of some of the efforts that you've done in previous years, and I didn't really see it get talked about much, but it was the effect of smoke and particulates and the various constituents in the smoke on the public. And I'm wondering, last year, I think we used, but didn't really socialize it that much, is that effort from, I think it was University of Boulder, Colorado, where they were modeling the smoke and able to project, a day or two or three out in front. And they actually did that for a fire for us out at the State Guard. Is that an area of interest and effort that you see coming in this coming fire season again? And what opportunities might there be? Because as you know, I've been reaching out to Health and Human Services and CDPH in there, and they have a strong interest in understanding what can be done on that protecting communities part, which is something I know that your seminar here brought up many times. Could you elaborate?
Yeah, I think there's a lot of work on the smoke and atmospheric composition. There's quite a few efforts on the Wharf S fire advancements and improvements, and some complementary atmospheric work with DOE and a variety of people that have been talked on here, NOAA. And I just got off the phone with someone, the BurnX exercise, where we last season, where we actually introduced some of those into the practice, I think is scheduled for July of this year. So it may be that, again, whether it's low-hanging fruit or some simple things, the idea of looking at perhaps a case study that could be done still within the context of that exercise and also that health linkage. We're certainly still working across the agencies on the health with, we have a data workflow figured out to go from atmospheric fire monitoring all the way to health epidemiology impacts. So it could be an example of pulling that out and basically asking people here is, where do you fit into that data flow, and perhaps trying to just see if we can exercise some of that this year.
No, thank you for that. Yeah, it almost seems like a combination of disciplines that would come together to work on this particular problem, where remote sensing is absolutely, an integral part of that, but you bring in the weather people and the public health people, but you end up with some easy to understand, do you stay indoors or can you go outside kind of output? Yeah.
Yeah, I mean, not trying to ask for anything too complicated, but the idea that a lot of people here say, I've got this, but can we start, and we know where, some are selling their services to and things like this, but it seems like there's some integration pieces that we could practice. Did anyone else have any thoughts here? And if Everett and Vince or anyone else, want to get a small team of people together to see if there's some there.
Yeah, I certainly think we could bring some people together from the, the health community and let's see, weather and then remote sensing to see what the synergies are and where there's common interest and needs there.
Ever just to add something to that request of mine was that I had reached out to Health and Human Services, the public health folks in California and this region, because the idea of a clearinghouse, there was this group that seemed interested in developing a wildfire clearinghouse analogous to what we have for a California earthquake clearinghouse. But I was excited when their senior management said, hey, this clearinghouse idea is something we are very supportive of. And then I saw HHS bring in other regions in terms of their interests. So then the question would be, well, what are the kind of products and capabilities that might be introduced in that way? So I just wanted to add there was a very interested group of people on this topic.
So I'm wondering what type of things would be served in a clearinghouse like that? What would be the envisioned?
Analogous to what the earthquake clearinghouse does, this kind of wildfire clearinghouse with a focus on public health. What we did a lot of is socialize what information agencies have, where to go to get it. We have speakers from different departments explaining specifics on, effects of wildfire, what you can do, where you should go. So it's kind of like bringing up the knowledge base. There are things that we don't do right now, like show the areas of land that have been exposed for long periods of time to high levels of smoke. So that's a kind of thoughts along of what a clearinghouse might do.
I see. Yeah, thanks for that. Steve Moran from Breezometer.
Yeah, just a comment. I've been talking with Pete Lamb, who works for Jerry Perez with the Forest Service, and he is focused on the air quality impacts of wildfire smoke. So he would want to participate in something like this too, I think, if it's going to have that aspect to it.
Yeah, and in fact, he's probably the first person I should, you know, have a conversation with just to get a sense of what he's been working on. I know Pete, and so yeah, that would probably be a good first step. I'm taking notes here, but this is also being recorded, so this is really, to me, this is sort of the heart of the whole meeting, is having these open conversations to pick over the presentations and look where there may be opportunities to look for improvements. And so yeah, I'm in the middle of my notes here. Birgit, are you aware of any folks that are involved with smoke modeling, public health, downwind issues, things like that?
I know we have a few at the survey who've linked with others out in the field. I'm trying to come up with a couple of names and looking through my emails. But yes, there are folks who are, at least within the survey, who are working in that arena.
Okay. I'll make a note there.
So if there, oops, am I still muted?
Nope, you're there. I heard you.
Yeah. So I just put in the chat, actually, I pasted a picture from the, so there is an interagency committee, but others can certainly be participating in this, and we can double check who some of the reps are. But we've actually been doing this wildfire data integration for health outcomes, and what's depicted in there was kind of what kind of data collected from different communities, then kind of follow the workflow. So you start out with things like land use and topography, and you pick up the, look at the WUI, and then you get, the weather information and the intensity of the fire. Then you pick up the smoke. The smoke feeds into the air quality. Then that moves over to the inhalation exposure people, who then get it into the data for people who have, asthma and other things, and then it, spits out at the other end of, these are the people in the fire area or downstream who are likely susceptible to the fire. And so if we had some airborne and a few other things, and you just said, hey, I spoke to Steve and his the breeze stuff and a few other things, and if you've got, here's some tools we have, here's some airborne assets, here's some satellite stuff, and why don't we see if we can, follow this flow of connecting our information from, the goal is put our information at different points here and see if we can spit out that health outcome at the other end.
I have a question for Steve Moran. There's a website, I think it's Fire Air Now, or I forget, but it's the place that I go to look for smoke patterns across the U.S., and it shows air quality monitors and the quality of the air at those different locations. I don't recall if breezometer is connected to those, to that map. Steve, if you're talking.
I'm pretty sure we are not.
Okay.
Yeah.
I'm trying to remember who I spoke to that was connected to that.
No, we do the Apple weather app air quality data, and which includes wildfire smoke, but no, we're not yet connected to EPA Air Now. They may use the same model we use, which is just the NOAA HRRR smoke model.
Right. Is let's see, Tom Rankovins from NOAA Online? I saw him this morning. I guess not. Any other thoughts? We're kind of bumping up on our break here, and I'd really like to give people a chance to get up and stretch their legs, and folks in the mountain time zone to get their lunch or whatever. So let's see. Let me just check my schedule. We're down to our last block, which will be picking up at 3:15 East Coast time, so roughly 25 minutes from now. Birgit or Vince, any other thoughts or questions? I took some good notes here, and I'll have the recording to refer back to because I'd like to do some deeper digging through some of the comments and conversation here. Kristen Allison also mentioned Sim Larkin from Air Fire Team would be a good person to add. So let me write that down.
Yeah, and Scott Kaplan posted the Air Now website.
Thanks for that. I couldn't remember the exact linkage for that.
Yeah, it's pretty simple. airnow.com.
You know, Everett, what was exciting to me, Phil Balin here again, was that you guys put together, have been putting together information like the effects of or potential for debris flows to occur after fires. And I saw this year really, or last year, really excitedly that counties were actually evacuating people or warning people, you know, to see that kind of science go into decision making was really exciting. So in my mind, a similar situation in this air would be, you know, an ability to show what will, you know, the air be like in the next day or two or three in terms of quality, so that, you know, parents, communities could find appropriate resources to keep in. It's hard to do it day by day. But again, just to point out that I was excited to see, you know, some of the science you guys have been talking about for a couple of years here put into that kind of practice, you know, in government. So,
well, thanks, Phil. And could you send me an email with just sort of just a couple lines of what you were suggesting so that I can build some thoughts around that?
Of course, I'd be happy to. Thanks.
And Scott Kaplan also posted some links there in the chat. I think we're going to go ahead and break so that we can. This is a little bit shorter of a break, so I'd like to give people a chance to get up and stretch their legs and whatever needs to be done, and be back here in about 21 minutes or so, and we'll pick up with Jack Gill and the Purdue team.
Hey, Everett, do we have a video to stream during the break, or you want to do that at a later point?
I didn't really have a chance to pull.
Okay.
Yeah.
All right. We'll just go.
One thing, I don't know if Mark Zoller's online, but he had a PowerPoint slideshow set up that can run automatically if you want to grab the screen here and run that during the break.
Yeah, that's her open download, so you can just pull that and it'll run automatically.
Yeah, I sent an email earlier that I didn't have the password access to that, so.
Right, and I've since opened it up to everybody.
Okay. Okay, well, let me give it a quick shot here, and so
And
Scott
while
says.
you're doing that, Everett, I might let everybody know that you'll see at the bottom of the agenda block 7.1 through 7.4, and those were additional presentations that we had that we didn't have slots for, but we always try to make those presentations available and to the community to understand the various other topic areas that we're covering under the 2-day limited agenda space that we have. So those presentations are available and will be available at the NIFC website as well. So just consider them to be add-ons to the program that don't naturally have a speaking slot. So thanks for that. And I'll let Everett do the video if he can get it up.
Yeah, I'm gonna just disconnect the share here for a minute and go look for that. So I'll be right back. Mark Zoller.
Is that downloading for you now, Everett?
I got a, it says no internet, but I know that I have internet, so. It looks like.
You're breaking up a little bit, like maybe your internet is bad.
Well, it was when I tried to access that. I'm going to skip the file for now, Mark, but
Yeah, okay, thanks for trying.